Picture a ship. Not the kind we build today, not the ISS with its 6 bunks and its resupply schedules and its emergency return capsule always docked and ready. Something different in kind, not just in scale. A vessel large enough to carry a population, autonomous enough to sustain itself without any contact with the world that built it, durable enough to function not for years or decades, but for centuries, possibly longer. The people aboard would be born there, they would grow up there, they would fall in love, raise children, grow old and die there, never having seen Earth except in recordings, never having stood under an open sky, never having felt rain. The destination would be a star, not metaphorically, an actual star, 4 or 40 or 400 light years away, toward which the ship moves at a fraction of the speed of light, while generation after generation lives and dies in the space between departure and arrival. This is the generation ship, one of the oldest concepts in serious thinking about interstellar travel, and one of the least resolved. Not because the engineering is intractable, though it is extraordinarily difficult, but because the deeper problem isn't engineering at all. The deeper problem is this: how long can a small, isolated human community remain functional? Not functional in the mechanical sense, though that too is uncertain. Functional in the human sense. Genetically viable, psychologically coherent, socially stable. Technologically competent across dozens of consecutive generations, each of which inherits a mission it never chose and a destination it will never reach. Each of which must maintain complex life support systems it may not fully understand, using knowledge passed down from people who are now dead, in service of a goal that may have transformed beyond recognition by the time the ship finally arrives. That is the real question. Not whether the engines can work, whether the people can. Tonight, we're going to follow that question honestly. We will look at the specific biological, psychological, sociological, and engineering constraints, at the actual numbers, the actual studies, the historical analogies, the proposed solutions and their limitations. We will try to give an honest answer to how long a generation ship could realistically survive. Not a hopeful answer, not a pessimistic one, an honest one. If you put this on because the night is long and you need something to settle into, stay. The generation ship is one of those subjects where following the questions carefully leads somewhere unexpected, somewhere that says something real about what we are as a species and what it would actually cost to carry that across the void. Let us begin with genetics, because it is the most unforgiving of all the constraints, and the one least amenable to engineering solutions alone. A generation ship carries a small population. It must be small. Every kilogram aboard represents fuel, mass, cost. Every additional person requires food, water, air, medical supplies, living space. You cannot simply add people to avoid genetic problems without proportionally scaling everything else: the ship's mass, its energy requirements, its complexity. There is a hard tension between the population size that genetics demands and the population size that engineering permits. And genetics demands more than engineering wants to give. Here is the fundamental problem. In a large open population, a city, a nation, a species, harmful recessive alleles are diluted. A recessive allele causes disease or reduces fitness only when a person carries 2 copies, one from each parent. In a large population, the probability that 2 carriers of the same rare, harmful allele will pair and produce offspring with 2 copies is low. The allele persists in the gene pool, but causes relatively little damage. In a small, closed population, that probability rises quickly. As generations pass, the same alleles cycle through a shrinking number of lineages. Relatedness between potential partners increases simply because there is no one left who is not already a cousin of some degree. Children of related parents are more likely to inherit 2 copies of harmful recessives, expressing diseases and physiological deficits that in a large population would have remained hidden. This is not speculation, it is documented in every isolated human population that has been studied carefully. Island communities show elevated rates of specific genetic diseases. Founder populations, religious communities that separated from the broader gene pool centuries ago, carry concentrated genetic disorders in their descendants. Wildlife in isolated reserves suffer measurable fertility and immune function decline from inbreeding. The biology is consistent and well understood. The second genetic threat is drift. In a large population, random variation in reproductive success averages out. No single individual's death or unusual fecundity moves the needle on overall allele frequencies in any meaningful way. In a small population, chance dominates. A beneficial rare allele can simply disappear because its carrier happened to die young or not reproduce. A harmful allele can become common simply because its carrier happened to have more surviving children in a particular generation. Over time, genetic drift reduces diversity. The population becomes more homozygous, more likely to carry 2 identical copies of any given allele, which amplifies the inbreeding problem. And the diversity lost to drift cannot be recovered from within. It is gone from that lineage permanently. The third threat is the bottleneck. Any event that substantially reduces the population, disease, accident, catastrophic system failure, social collapse, creates a genetic bottleneck from which the recovering population carries only the alleles present in the survivors. Diversity lost in a bottleneck cannot be regenerated internally. Every subsequent generation inherits a narrower genetic foundation than the one before the event. On a generation ship, bottleneck risk is continuous. Every major crisis, every epidemic, every explosion, every failure of a critical life support system is a potential bottleneck. And generation ships will have crises. The question is not whether, but how many, how severe, and whether the population can absorb them without irrecoverable genetic narrowing. How large does the founding population need to be to avoid these problems across centuries of travel? This has been the subject of serious quantitative analysis. A 2002 study by Camilla Smith at the University of Michigan calculated a minimum viable population for a multi-generational voyage of approximately 160 individuals, the number required to maintain sufficient genetic diversity over a journey of several hundred years, assuming well-managed mating practices. This number was widely cited and subsequently criticized as too optimistic. More recent modelling by Frolov and Morozov in 2014, using more sophisticated population genetics simulation, suggested numbers an order of magnitude larger, somewhere between 2,000 and 10,000 individuals, for journeys measured in thousands of years. The discrepancy between 160 and 10,000 is not a rounding error. It reflects genuine uncertainty about how genetic diversity degrades under specific assumptions about journey length, breeding practices, bottleneck events, and the initial genetic composition of the founding group. What can be said with reasonable confidence is this: smaller founding populations carry higher genetic risk. The risk compounds over time, and every bottleneck event increases the risk for every subsequent generation. A ship that begins with 500 people and survives a disease that kills 200 of them is not simply smaller, it is genetically narrowed in ways that cannot be undone. Technological interventions can reduce but not eliminate these risks. Frozen gametes, eggs and sperm from a large and genetically diverse donor population on Earth, could be carried aboard and used to introduce new variation into the ship's gene pool at intervals. This effectively expands the functional gene pool far beyond the number of living people aboard. Frozen embryos could similarly be gestated by surrogate mothers aboard. Gene therapy, direct editing of the genome in living people, represents a more speculative but not physically impossible intervention. Each of these solutions introduces its own dependencies. Frozen gametes require cryogenic preservation at temperatures near absolute zero, maintained reliably across centuries. Frozen embryos require both cryogenic infrastructure and the medical capability to carry and deliver them. Gene therapy requires biotechnological capabilities that do not yet exist at the scale required. These are not insurmountable obstacles in principle, but each is an additional system that can fail, an additional technical competency that must be maintained and transmitted across generations. Now let us talk about psychology, about what long-duration isolation actually does to human beings, and why the psychological literature on this subject is consistently more troubling than popular treatments of the generation ship concept acknowledge. The most instructive data we have comes from several distinct research traditions. Antarctic winter-over studies, where small groups of people spend 6 to 14 months in near-total isolation at research stations, provide one window. Nuclear submarine service, where crews of 50 to 150 people spend months submerged with no contact with the outside world, provides another. Long-duration spaceflight aboard the ISS, and before it, Mir, provides a third. And the Mars 500 isolation study, in which 6 men lived for 520 days in a simulated spacecraft module in Moscow, provides the longest controlled isolation experiment ever conducted. The findings across these very different contexts are strikingly consistent. Monotony is a serious and underappreciated stressor. Humans are adapted for environments with variation, changing landscapes, changing social contexts, changing sensory stimuli. Environments with minimal variation produce measurable psychological degradation over time. Increased irritability, decreased motivation, cognitive slowing, disrupted sleep, flattened affect. The Antarctic winter-over syndrome is well documented, a cluster of symptoms including depression, cognitive impairment, and interpersonal conflict that appears with remarkable regularity in isolated winter stations. Social tension is essentially inevitable in small groups under prolonged confinement. Research on groups in isolated environments consistently finds the formation of cliques, the emergence of interpersonal conflicts that persist and escalate in ways that would not occur in open social environments where exit and avoidance are options, and the disproportionate psychological impact of a small number of difficult individuals who cannot be avoided or replaced. The third quarter phenomenon, a documented decline in morale and performance occurring approximately 3/4 of the way through a defined mission, appears across multiple contexts and appears to be driven by the psychological difficulty of the period when initial motivation has faded, but the end is not yet in sight. On a generation ship, there is no third quarter. There is no defined end for the people living through it. The destination is not a date on a calendar, but an inheritance belonging to their descendants. What happens to motivation, to psychological well-being, to the functional capacity of individuals when the confinement is not temporary but permanent? when there is no end in sight because the end belongs to people not yet born, is unknown. Mars 500 lasted 520 days. That is not a generation. It is not a decade. It is not a lifetime. Extrapolating from 520 days to 500 years is not a linear operation. 2 of the 6 Mars 500 participants spent large portions of the 520 days in what researchers described as sedentary behavior, significantly exceeding normal baselines, effectively hibernating, withdrawing from social interaction, sleeping excessively. This was not a planned response to confinement. It appeared to emerge spontaneously as a coping mechanism, a kind of psychological retreat from an environment offering insufficient stimulation. If this pattern appears at 520 days, what does it look like at 5 years? At 20? The generation ship literature in serious fiction has repeatedly converged on the same psychological disaster scenarios. Populations that forget the mission, individuals who retreat into passivity or into obsessive behavior patterns, social structures that calcify around the specific conditions of confinement in ways that become dysfunctional at the destination. These are not arbitrary, imaginative inventions. They are reasonable extrapolations from documented human psychology in isolated environments. Now let us talk about social structure, about what happens to human societies across multiple generations of total isolation, and why the historical record on this is not encouraging. Every isolated human community that has been studied over multiple generations has transformed significantly from its founding state. This is not surprising. Cultural evolution is a universal feature of human societies. What is relevant for the generation ship is the specific character of the transformation, and whether the transformations that occur in isolated communities are compatible with the technical and social requirements of the mission. The Pitcairn Island case is instructive. In 1790, 9 British mutineers from the Bounty and 18 Polynesians, 6 men, 12 women, settled an uninhabited island roughly 5,000 kilometers from the nearest significant landmass. The founding population was small, the isolation near total, and the early history marked by violence. Within a few years of landing, murders had reduced the male population to a single surviving mutineer, John Adams, living with several women and children. From that bottleneck, genetically and socially catastrophic by any measure, a community grew. By 1856, it had reached 193 people and needed to be relocated because the island's resources were insufficient. Today, approximately 50 people remain. The community is genetically narrow, has documented elevated rates of several hereditary conditions, and speaks a Creole that blends 18th century English with Tahitian, unrecognizable to speakers of either ancestor language. The Pitcairn case demonstrates several things relevant to the generation ship. Small founding populations can survive and grow even from extreme bottlenecks. Isolation rapidly produces cultural and linguistic divergence. Violence and social conflict are persistent risks in extreme isolation, and genetic narrowing has real health consequences that accumulate over generations. Easter Island presents a darker trajectory. Polynesian settlers arriving around the 4th to 9th century CE built a sophisticated civilization capable of quarrying, transporting, and erecting multi-ton stone statues across difficult terrain, an achievement requiring complex social organization, technical knowledge, and sustained collective effort. Then, over a period whose precise timing remains debated, the civilization collapsed. The population declined severely. The technical knowledge that built the statues was lost. When Europeans arrived in 1722, they found a fractured society using the statues as rubble. The traditional explanation, environmental overexploitation leading to deforestation and loss of the ability to build canoes, trapping the population on a dying island, has been complicated by more recent research implicating European disease and slave raiding as significant factors. The truth is probably a combination, but the core lesson remains. An isolated civilization can undermine its own resource base, and the technical knowledge on which complex achievements depend can be lost entirely within a relatively small number of generations. For a generation ship, the Easter Island analogy is specific and serious. The ship's resources are finite. The technical knowledge on which survival depends is complex. Both can be degraded, the first by poor management, the second by inadequate transmission across generations. And on a generation ship, unlike Easter Island, there is no possibility of rescue from outside. The islanders who lost the ability to build canoes were at least still breathing the atmosphere of their world. A generation ship crew that loses the knowledge to maintain its life support systems has no equivalent fallback. Now let us talk about the specific engineering challenge of maintaining a closed life support system over centuries, about what Biosphere 2 taught us and what it implies about the difficulty of the problem. Biosphere 2 was the most ambitious attempt ever made to create a self-sustaining, closed ecological system. Built in the Sonoran Desert in Arizona, it enclosed approximately 1.3 hectares of habitat in a sealed glass structure containing agricultural land, a small ocean, a rainforest, a savanna, a marsh, and a desert. In 1991, 8 people entered the sealed structure for a planned 2-year stay, with the goal of living entirely on what the system produced. The system failed to support them. Within the first year, oxygen levels fell from 21% to approximately 14%, comparable to an altitude of roughly 4,300 meters. Participants experienced cognitive impairment, fatigue, and difficulty concentrating. The cause was eventually identified as unexpected oxygen consumption by microbes in the soil, an interaction between soil chemistry and the concrete structure that had not been modeled correctly. Oxygen had to be pumped in from outside to maintain survivable levels. Food production was chronically insufficient, despite the agricultural land, and despite the participants devoting significant time to farming. By the end of the 2 years, most participants had lost substantial body mass, around 16% on average. Caloric intake was consistently below what was needed. Biosphere 2 had the benefit of being on Earth, embedded in the largest research institution in history, with the ability to make adjustments and, in the ultimate emergency, break the seal and let people out. None of these safety nets exist on a generation ship. The specific lesson of Biosphere 2 is not that closed life support systems are impossible. It is that they are more complex than they appear, that unexpected interactions between system components produce problems that no model predicts, and that the margin for error is smaller than intuition suggests. A closed ecological system designed by the most careful team in history, tested with the most extensive preliminary modelling available, failed to support 8 people for 2 years, under conditions far more favourable than any generation ship will face. Scaling this to a ship supporting thousands of people for centuries requires not just better engineering, but qualitatively different engineering. Systems with redundancy at every level, with self-diagnostic capabilities, with the ability to identify and correct failures that no designer anticipated. Whether such systems are achievable is not physically impossible, but no version of them has yet been built. The water recycling problem is illustrative. The ISS recovers approximately 93% of water from urine and humidity, a genuine engineering achievement. But 93% efficiency means 7% loss per cycle. On the ISS, that loss is compensated by resupply missions. On a generation ship, resupply is impossible. At 93% efficiency, even a modest amount of leakage from the system would cumulatively deplete water reserves over decades. Getting to 99.9% efficiency, which may be necessary for a centuries-long voyage, has never been achieved in any system operating at relevant scales. The same logic applies to atmospheric composition, soil fertility in agricultural systems, microbiome stability, and essentially every other component of a closed life support system. Every efficiency shortfall compounds over time. Every unexpected interaction between system components produces a problem that must be diagnosed and corrected. Every repair requires knowledge, tools, and spare parts, all of which must be carried or manufactured aboard. Now let us talk about the problem of knowledge transmission, about how technical expertise degrades across generations in isolated communities, and why this may be the most underappreciated risk the generation ship faces. Our technological civilization is extraordinarily complex. The smartphone in your pocket contains components manufactured in dozens of countries, from materials mined on 6 continents, using techniques developed over centuries of accumulated scientific progress. No small, isolated group can replicate anything approaching this complexity. A generation ship must carry not just people and machines, but knowledge, the entire technical corpus required to maintain the ship's systems and to address novel problems as they arise. This is not merely a matter of having databases available. It is a matter of skills, competencies, and practical understanding that can only exist in people, that must be learned and practiced and transmitted, and that degrade if they are not. Consider a concrete example. Suppose the ship's propulsion system requires specialized knowledge of plasma physics for maintenance and occasional repair. This knowledge must exist in the ship's population at every generation throughout the voyage. If one generation fails to transmit it adequately to the next, whether through cultural drift, psychological disruption, simple accident, or the death of the relevant specialists before they train successors, the knowledge is lost. It cannot be recovered from within. Historical evidence for this kind of knowledge loss in isolated communities is extensive. The inhabitants of Easter Island lost the ability to build ocean-going canoes, a technology their ancestors had mastered well enough to sail thousands of kilometers of open ocean. Medieval Europe lost significant Roman engineering knowledge, including concrete formulations and aqueduct maintenance techniques. The specific methods used to construct the Parthenon were lost for centuries. In each case, a technology that had been reliably practiced became inaccessible within a relatively small number of generations, in communities significantly larger than any realistic generation ship crew. The mechanism is consistent. Technical knowledge requires not just recording, but active transmission through practice. A written description of how to perform a complex procedure is not the same as the embodied knowledge of someone who has performed it many times and been corrected by someone who performed it before them. When the chain of practice breaks, when there is no one left who has actually done the thing and who can teach someone else to do it, the written record becomes increasingly difficult to use correctly without that embodied foundation. On a generation ship, every technical domain required for survival must have an unbroken chain of practice transmission across every generation of the voyage. A single break in any critical chain is potentially fatal. And the ship cannot call for help. There is no institution outside itself that can send a specialist. Whatever knowledge is lost permanently. Now let us talk about governance, about the specific challenge of designing decision-making structures that remain functional across generations of total isolation. and that protect critical technical functions from the predictable dynamics of human political behaviour. Every human community requires mechanisms for making collective decisions, resolving conflicts, and establishing norms. On a generation ship, this problem has several features that have no analogue in any existing human institution. There is no external authority, no court of appeal beyond the ship's own structures, no international community to exert pressure, no exit option for dissidents. Whatever governance system operates aboard the ship is the only governance system there is, and whatever failures it produces must be addressed entirely from within. The governance system must persist across generations that did not choose it. The founding generation designed the system and consented to its constraints. The second generation was born into it. The 20th generation inherits it as a given. The rules under which they live, whose original rationale may be entirely unknown to them. Rules that were initially functional may have become ritual by the time their purpose is forgotten. Critical technical decisions, maintaining the life support systems on schedule, preserving genetic diversity management protocols, not diverting propulsion resources for other purposes, must be protected against short-term democratic pressure. A vote to reduce agricultural maintenance in favour of more comfortable living space may make immediate sense to the people casting it. The consequences may not appear until the next generation. Democratic systems are poorly suited to protecting future generations from decisions that benefit present ones at their expense. But the alternative, a technical elite with unilateral authority over critical systems, creates concentration of power that historically corrupts. Technical knowledge becomes a basis for social dominance. The interests of the knowledge-holding class diverge from the interests of the broader population. Resentment accumulates. The most sophisticated proposals for generation ship governance involve constitutional structures that place critical technical functions beyond ordinary political reach, making them more like laws of physics than policy choices, embedded so deeply in the ship's cultural and institutional fabric that changing them requires extraordinary consensus rather than ordinary voting. Combined with democratic governance for everything else, and with cultural systems that treat technical competence as a sacred social obligation rather than a source of privilege, whether such a constitutional structure can actually persist across 20 or 50 generations of isolation, without either calcifying into something dysfunctional or being dismantled by populations that have forgotten why it was designed, is unknown. No institution on Earth has maintained equivalent stability under equivalent conditions. The longest-lived human institutions, the Catholic Church, the Japanese imperial system, certain legal traditions, have persisted for centuries or millennia, but all of them have had continuous contact with the broader world. None has operated in total isolation. None has had its survival depend on maintaining specific technical functions correctly. This is perhaps the core of what makes the generation ship problem so hard. It is not one problem, but a set of interlocking problems: genetic, psychological, sociological, technical, each of which is individually serious and each of which interacts with all the others. A genetic bottleneck from a disease outbreak also depletes technical expertise. A governance failure that diverts resources from life support maintenance also affects food production. A cultural drift away from scientific rationalism also compromises the ability to diagnose and repair engineering failures. The problems compound each other in ways that make the whole significantly more difficult than any individual component. Now let us talk about the realistic parameters of a generation ship voyage, about what specific numbers look like under different technological assumptions, and what those numbers imply. The nearest star system, Alpha Centauri, of which Proxima Centauri is a component, is 4.24 light-years away. At Voyager 1's current speed of approximately 17 kilometers per second, a ship heading for Proxima Centauri would take approximately 73,000 years to arrive. This is not a generation ship in any meaningful sense. It is a species-scale project involving tens of thousands of generations and timescales on which human biology itself would evolve. For a generation ship to be a recognizable project rather than an evolutionary process, the travel time needs to be measured in centuries rather than millennia. This requires propulsion significantly beyond anything currently available. At 1% of the speed of light, achievable in principle with nuclear pulse propulsion concepts that have been seriously studied though never built, travel time to Proxima Centauri would be approximately 430 years. That is roughly 15 to 17 human generations, assuming an average reproductive age of 25 to 30 years. Long enough for every problem we have discussed to be real and serious. Short enough that biological evolution is not a significant factor. This is the canonical generation ship scenario. At 5% of the speed of light, requiring propulsion substantially beyond nuclear pulse, likely involving fusion or some form of laser-driven sail, travel time would be approximately 85 years. This is within or close to a single human lifetime, depending on life extension technologies available at departure. The multi-generational problem largely disappears, though the isolation problem remains severe. At 10 to 20% of the speed of light, requiring antimatter propulsion or some other technology with no current engineering basis, travel time falls to 20 to 40 years. This is a single-generation mission in terms of personnel, though still extraordinarily demanding psychologically. The relevant range for a true generation ship is probably 1 to 5% of the speed of light, with travel times of 85 to 430 years and crew sizes of several thousand people. At the lower end of travel time and upper end of crew size, the problems we have discussed become more manageable. At the upper end of travel time and lower end of crew size, they become extremely severe. Every calculation about minimum viable population, about knowledge transmission, about psychological sustainability, about governance stability, every one of these calculations is sensitive to both duration and crew size. The problem is not fixed. It scales, and it scales in the wrong direction. Longer voyages need larger crews for genetic reasons, but larger crews need more resources, and more resources require larger ships, and larger ships require more sophisticated propulsion, and more sophisticated propulsion requires more knowledge to maintain. These are not independent variables. They are coupled in ways that make optimization across all of them simultaneously extraordinarily difficult. Now let us talk about what would need to be true for a generation ship to succeed. Not what we wish were true, but what the analysis actually demands. The founding population would need to be large enough to maintain genetic viability across the full duration of the voyage, with realistic modelling of bottleneck probabilities rather than optimistic assumptions about smooth population growth. This probably means several thousand people at minimum, augmented by extensive frozen genetic material. The life support systems would need to be built with redundancy and self-diagnostic capability far beyond anything currently demonstrated. Not just with backup systems, but with the ability to identify novel failure modes and respond to them without requiring specific expertise that may not exist in the crew at the moment of failure. The knowledge transmission systems would need to be designed as explicitly as the mechanical systems, with formal structures for identifying critical technical competencies, ensuring their transmission across every generation, and detecting gaps before they become lethal. This probably requires a dedicated technical class whose role and status are protected by cultural and institutional mechanisms strong enough to survive significant social disruption. The governance structure would need to protect critical functions against democratic erosion, while remaining legitimate enough to prevent the resentment that produces mutiny. This is a genuine design problem, not a rhetorical flourish, and it has no obvious solution from existing political theory. The cultural system would need to provide meaning, motivation, and psychological stability for people who were born into a mission they did not choose and will die without seeing completed. This is perhaps the requirement for which we have the least guidance, and the one that may ultimately be most decisive. None of these requirements is individually impossible. Each has been approached, if not achieved, in some context on Earth. But achieving all of them simultaneously, maintaining that achievement across multiple centuries of total isolation, and doing so with a closed system that cannot draw on any external resources, this is something that has never been attempted, and whose difficulty it is easy to underestimate. The honest answer to how long a generation ship could survive is probably not as long as needed, unless we understand the problems significantly better than we currently do and invest seriously in closing the gaps. The technical gaps are real but bridgeable with sufficient engineering effort. The human gaps, genetic, psychological, sociological, cultural, are less amenable to engineering solutions and more dependent on developing understanding we genuinely do not yet have. This is not a reason to abandon the concept. It is a reason to take the human side of the problem as seriously as the mechanical side, to invest in the research that would actually close those gaps. To resist the temptation to treat the generation ship as a solved problem waiting only for propulsion technology to catch up, it is not a solved problem. It is a problem waiting to be taken seriously. Let us talk about the specific problem of radiation, about what the interstellar environment actually looks like from a dosimetry perspective, and why the radiation threat to a generation ship is qualitatively different from the radiation threat faced by astronauts on shorter missions. Inside the solar system, the heliosphere provides partial shielding from galactic cosmic rays, the high-energy particles originating from supernovae and other violent processes throughout the galaxy. As Voyager 1's measurements confirmed after its 2012 heliopause crossing, galactic cosmic ray intensity outside the heliosphere is approximately 10 to 20% higher than inside. Not dramatically higher, but consistently, persistently higher, with no solar cycle variation to provide even partial relief. A generation ship leaving the solar system would spend the vast majority of its voyage in this unshielded interstellar environment. Galactic cosmic rays are not like solar radiation. They cannot be blocked by modest shielding. They consist primarily of protons and heavier nuclei accelerated to energies of millions to trillions of electron volts. At these energies, most shielding materials simply produce secondary radiation cascades. The incoming particle strikes a nucleus in the shield and produces a spray of secondary particles that may be more biologically damaging than the original. The only effective shield against galactic cosmic rays is mass, substantial mass, meters of water or polyethylene or regolith, enough to absorb and dissipate the cascade. NASA's estimates for adequate cosmic ray shielding for a Mars mission, a journey measured in months, already suggest requirements that challenge mission design. For a journey measured in centuries, the cumulative dose implications are severe. Current NASA career radiation limits for astronauts are set at levels intended to keep excess lifetime cancer risk below 3%. A generation ship crew member spending their entire life 70 to 80 years in the interstellar cosmic ray environment without adequate shielding would accumulate doses exceeding these limits by substantial margins. Every generation would face elevated cancer rates, elevated rates of radiation-induced cataracts, and emerging evidence suggests elevated rates of cognitive decline from chronic low-level radiation exposure to the central nervous system. This is not a crisis in the sense of acute radiation sickness. It is a chronic degradation, a consistent elevation in disease burden across every generation of the voyage. The medical systems aboard must be capable of managing elevated cancer rates indefinitely. The population models must account for reduced life expectancy and reduced work capacity in a fraction of the crew at all times. The genetic impact of radiation-induced mutations accumulating across multiple generations adds another layer to the genetic risk picture. The engineering response, heavy shielding around the most critical habitation spaces, creates a mass problem. Every additional metre of water shielding around a habitation module adds tons per square metre of surface area. For a ship housing thousands of people in enough volume to sustain psychological health across generations, the shielding mass could easily dwarf the mass of everything else aboard. This drives ship designers towards solutions involving in situ resources, using water already required for drinking and agriculture as structural shielding, positioning denser systems like fuel and machinery on the ship's outer hull to provide incidental shielding, designing ship geometry to minimize exposed surface area per unit of habitable volume. None of these approaches eliminates the problem. They manage it at significant design cost, to a level that may be compatible with multi-generational survival, but compatible with elevated disease burden, not with a crew that experiences radiation exposure equivalent to life on Earth. The radiation problem is one of the clearest examples of how the generation ship challenge compounds across domains. It is not just a physics problem or an engineering problem. It affects medical system requirements, population demographic modelling, genetic risk assessment, and the psychological burden of a crew that knows every member carries elevated cancer risk from birth. All of these feed back on each other. Let us now talk about food, about what it actually requires to feed a closed population across centuries, and where the specific vulnerabilities lie. Modern agriculture is significantly more complex than it appears. The productivity we take for granted depends on specific crop varieties selected over millennia of cultivation, on soil microbiomes built up over long periods, on pest and disease management systems that draw on external inputs, on controlled irrigation, on mechanized harvesting, and on global supply chains that allow any local failure to be compensated by imports from elsewhere. None of this applies to a generation ship. Every calorie consumed must be produced within the closed system. Every nutrient must be cycled back to the growing medium. Every pest outbreak, every fungal infection, every unexpected crop failure must be addressed from within. The nutritional completeness problem is particularly serious. Humans require a specific set of macronutrients and micronutrients, essential amino acids, essential fatty acids, vitamins, minerals, that cannot all be obtained from a small number of staple crops. Historical examples of nutritional deficiency in populations dependent on limited crop bases are instructive. Scurvy, vitamin C deficiency, devastated naval crews even when total caloric intake was adequate. Pellagra, niacin deficiency, was endemic in populations dependent on corn as a primary staple, because niacin in corn is bound in a form humans cannot absorb without specific preparation techniques. Beriberi, thiamine deficiency killed large numbers of people eating diets dominated by polished white rice. In each case, the deficiency appeared not because total food supply was inadequate, but because specific nutrients were absent from a limited diet. On a generation ship, diagnosing nutritional deficiencies requires medical knowledge and diagnostic capability maintained across generations. Correcting them requires either growing nutritionally diverse food, which requires agricultural area and agricultural knowledge, or manufacturing supplements, which requires chemical production capability. Either path requires sustained technical competence and physical infrastructure. The agricultural system also faces an entropy problem that is rarely discussed in generation ship literature. Soil fertility in agricultural systems is maintained on Earth by inputs from outside the cultivated area: weathering of mineral substrate, atmospheric deposition, incorporation of organic matter from uncultivated land. In a closed system, every mineral taken up by a plant and consumed by a person must eventually return to the agricultural substrate, or the system becomes progressively depleted. This requires not just composting food waste, but capturing and recycling every form of nutrient output, including human metabolic waste, with high efficiency, indefinitely. The efficiency with which nutrient cycles can be closed in artificial agricultural systems has been studied in the context of long-duration space missions. The numbers are not yet adequate for century-scale voyages without some form of mineral supplementation from an external source. Getting to the required efficiency involves solving problems in closed-loop biogeochemical cycling that remain open in the scientific literature. Let us now talk about the specific psychological problem of purpose, about how people find meaning in lives that are entirely defined by a mission they did not choose and will not complete, and why this is harder than it might appear. Meaning is not a luxury. It is a functional requirement for human psychological health. People deprived of meaningful purpose develop recognizable patterns of psychological deterioration, apathy, depression, increased susceptibility to addiction and self-destructive behavior, reduced cognitive engagement, reduced social investment. Viktor Frankl, whose analysis of survival in Nazi concentration camps produced one of the most influential psychological frameworks of the 20th century, argued that the capacity to find meaning, even in conditions of extreme suffering, was the primary determinant of psychological survival. On a generation ship, the mission provides a potential structure for meaning. The crew is doing something unprecedented. They are carrying humanity to another star. The stakes are as high as stakes get. For the founding generation, who chose this, the mission may provide profound and sustaining purpose. For the second generation, the connection is more tenuous. They did not choose, they inherited. The mission is the context of their lives rather than the project of their lives. Some will identify deeply with it. Others will experience it as a constraint, the walls within which they must live, the obligation they carry without having chosen it. By the fifth generation, the founding impulse is historical rather than personal. No one aboard has any memory of Earth, only records, only stories, only an increasingly distant origin that is becoming more mythological than experiential. The destination is equally remote, a place that their descendants will reach, not them. They live in the middle of something that started before them and will end after them, in a space defined entirely by a project to which they contribute, but which neither began with nor will culminate for them. What gives a fifth-generation crew member reason to get up in the morning and perform the maintenance work that their survival depends on? What gives them reason to master the technical knowledge required to keep the systems running? What gives them reason to make the social accommodations and individual sacrifices that closed community life demands? These are not rhetorical questions, they are design questions. The ship's designers must think carefully about what cultural systems, what narratives, what rituals, what social structures, what aesthetic experiences will provide adequate meaning for people living in these conditions. And those systems must be robust enough to persist across generations of cultural evolution in total isolation. Religious belief is probably the most powerful tool available for this purpose. Every major, long-lasting human institution whose survival has depended on maintaining specific practices across generations under difficult conditions has used religious or quasi-religious belief as its primary mechanism. The belief that one is participating in something cosmically significant, that one's work matters not just instrumentally but intrinsically, that one's sacrifice has meaning that transcends immediate reward, is psychologically very powerful and historically very durable. A generation ship whose culture has developed a deep and genuine religious relationship to the mission, where maintaining the life support systems is understood as a sacred obligation, where technical competence is a form of devotion, where the voyage itself has the character of a pilgrimage, has significantly better odds of maintaining the psychological and social cohesion required for survival than one that treats the mission as a purely technical project. This is not an argument for designing a false religion. It is an observation about what kinds of meaning systems tend to sustain human communities across long periods of difficulty, and a suggestion that the generation ship's designers should think seriously about cultural architecture alongside physical architecture. Let us now talk about the children, about what it is actually like to grow up on a generation ship, and what the developmental psychology of total confinement might produce. Every person born aboard a generation ship will develop within an environment that has no analogue in human evolutionary history. For several 100,000 years, human children developed in environments with open skies, with changing landscapes, with diverse ecosystems, with the full range of sensory experience that the natural world provides. The developmental scaffolding of human psychology was built in these environments. The stimulation thresholds, the attentional systems, the spatial cognition, the emotional regulation capacities were all shaped by evolution to function in open, varied, richly stimulating natural settings. A generation ship provides none of this. The sky is the ceiling of a habitat module. The horizon is a wall. The landscape never changes. The seasons are managed by programmable lighting systems. The wildlife is whatever the agricultural system requires for pollination or pest management. The full range of weather, terrain, ecological complexity, and natural unpredictability that human cognitive development is calibrated to navigate, absent. The psychological effects of growing up without access to natural environments are documented in children on Earth who live in highly urbanized environments with minimal green space. The effects include elevated rates of attention deficit, reduced capacity for stress regulation, impaired immune function, and measurably lower psychological resilience. These effects are observed in children who still live under real skies and who have at least intermittent access to parks, to natural light, to the outdoors. What the effects look like when the deprivation is total, when there is no natural environment of any kind, no open space, no unmanaged ecosystem, no sky, is not known, because it has never happened. The developmental psychology literature can identify the direction of the effect, but not its magnitude in the limiting case. There is also the question of physical development. Human musculoskeletal systems develop in response to the gravitational loading of Earth's 1G environment. Under reduced gravity, whatever partial gravity a rotating habitat provides, bones and muscles develop differently. Children growing up in 0.7G or 0.8G will develop skeletons and musculature calibrated to that environment. If they arrive at a destination planet with gravity significantly higher, if they land on a world with 0.9 or 1.0G after a lifetime in 0.7G, the adaptation will be painful and maybe only partial. After multiple generations in the ship's gravity environment, the gap between the crew's physiological calibration and the destination's gravity may have widened further, depending on how closely ship gravity is managed relative to the target planet's gravity. If the ship's designers underestimated the target planet's gravity, or if the gravity management systems degraded slightly over generations, the arriving crew may face a physical environment that their bodies are genuinely ill-suited for. Not just uncomfortable, but physiologically challenging in ways that compromise their ability to perform the work that establishing a colony requires. Let us now talk about something that very few serious analyses of the generation ship acknowledge directly: the probability distribution of outcomes, and what it implies for how the concept should be approached. The generation ship is not a binary proposition. It does not either work perfectly or fail catastrophically. It exists on a spectrum of outcomes, from complete success to total failure, with a large middle range of partial successes and partial failures, ships that arrive but with depleted genetic diversity, ships that arrive with surviving populations that have lost critical technical knowledge, ships that arrive with functional technology but psychologically damaged crews, ships that get most of the way there before a compounding series of failures ends the mission. A realistic assessment of the probability distribution across these outcomes requires quantitative estimates of the failure probability for each risk category: genetic bottlenecks, life support failures, knowledge transmission gaps, governance breakdowns, social collapse, and some framework for understanding how these failure modes interact. This kind of quantitative risk assessment has not been done comprehensively for the generation ship concept. The existing literature contains qualitative risk analyses and partial quantitative treatments of specific risk categories, population genetics modelling, life support reliability estimates, but not an integrated probabilistic model that combines all risk categories into an overall mission success probability. What such an analysis would likely show, based on the qualitative picture, is a wide probability distribution with a long tail toward failure. The most likely outcome of any given generation ship mission under current understanding is probably not clean success or rapid catastrophic failure, but some form of partial degradation over the course of the voyage, culminating in arrival in a state significantly compromised from the founding state. This does not mean generation ships should not be built. It means they should probably be built in numbers, multiple missions to multiple targets, accepting that some will fail, designed so that the successful ones can establish viable colonies without depending on any individual mission being perfect. This is how human expansion has always worked. The settlement of the Pacific was not a single perfect expedition. It was hundreds of attempts over centuries, with many losses, gradually filling the ocean with island cultures. The generation ship program of the future, if it happens, will probably look similar. Not one perfect ship, many imperfect ones. Enough of them arriving successfully to justify the whole enterprise. Let us now talk about the specific question of what advances would most improve the prospects of a generation ship. Not what we wish for, but what specifically would make the biggest difference and how achievable those advances are. reliable human cryopreservation would be the single most transformative development. If the entire crew can be frozen for the duration of the voyage, with a small rotating watch kept awake for maintenance, the multi-generational problem essentially disappears. One crew departs, one crew arrives. The psychological problems of perpetual confinement are eliminated. The cultural drift problem is eliminated. The knowledge transmission problem is dramatically reduced. The arriving crew has the same knowledge as the departing crew, just older. Cryopreservation of human beings, safe freezing and thawing without cellular damage, particularly without brain damage, has not been achieved. We can freeze embryos, oocytes, and some tissues. We cannot reliably freeze an adult human. Research continues, including work by private companies pursuing both medical cryonics applications and research into reversible suspended animation for long-duration spaceflight. The underlying biology is challenging, but not obviously impossible. Whether reliable whole-body cryopreservation is achievable is genuinely uncertain. Propulsion technology that reduces travel time to decades rather than centuries would be the second most transformative development. At 10% of the speed of light, achievable with sufficiently advanced fusion propulsion, a technology that has been studied seriously for decades, travel time to Proxima Centauri is approximately 43 years, within a human lifetime with life extension. The multi-generational problem is substantially reduced even without cryopreservation. Fusion propulsion is closer to achievable than whole-body cryopreservation in the sense that the physics is better understood and the engineering challenges, while enormous, are more clearly defined. Whether the timeline to fusion propulsion adequate for interstellar use is decades or centuries is uncertain. Advanced AI systems capable of maintaining technical knowledge and managing complex systems autonomously over centuries would substantially reduce the knowledge transmission problem. If AI can serve as institutional memory, holding the technical knowledge required to maintain ship systems and making it accessible to crew members who may not have been specifically trained in a given domain, the risk of critical knowledge loss is dramatically reduced. AI systems today are not adequate for this role. Whether they become adequate within relevant timescales is uncertain. Each of these advances would transform specific aspects of the generation ship problem. None of them transforms all aspects, and none of them exists in the required form today. The generation ship, even in a technologically optimistic scenario, is probably at least 2 to 3 centuries away from being seriously feasible, assuming continuous technological progress and sustained civilizational interest in the project. Whether those conditions will be met, whether human civilization will be intact and technologically advancing and motivated to pursue interstellar exploration 2 to 3 centuries from now, is itself deeply uncertain. Let us talk about something that technical analyses of the generation ship consistently underweight: the problem of boredom. Not boredom in the colloquial sense of having nothing to do on a Tuesday afternoon. Boredom in the deep, chronic, structural sense of living in an environment that provides insufficient novelty, insufficient stimulation, insufficient variation to sustain the psychological engagement that human beings require to function well over long periods. The human brain was not designed for stability. It was designed for a world that constantly presented new information, new terrain, new social configurations, new threats and opportunities, new sensory inputs. The neurological reward systems that drive human behavior are calibrated to respond to novelty, to change, to the unexpected. When novelty is absent, when every day presents the same visual environment, the same social group, the same tasks, the same constraints, Those systems adapt by lowering their baseline, reducing their sensitivity, withdrawing engagement from an environment that has stopped offering useful information. This is not a character flaw, it is a feature of a nervous system designed for open environments. The same system that drives relentless exploration and innovation in humans living in varied environments produces apathy, depression, and cognitive disengagement in humans living in monotonous ones. The generation ship is the most monotonous environment humans have ever designed. The same corridors every day, the same people every year, the same tasks every season. The same view from every window, which is not a view at all, just the blackness of interstellar space, with its stars too distant to visibly move. For an entire lifetime, for every lifetime aboard. Novelty can be introduced artificially. The ship can be designed with changing environments, variable lighting cycles, rotating agricultural zones, social spaces that transform seasonally, artistic installations that evolve over time. Structured programs of intellectual challenge, education, research, artistic creation, engineering problem solving can provide cognitive stimulation. Social novelty can be generated by the ship's own cultural evolution, by births and deaths and relationships and conflicts that are not scripted. But these artificial sources of novelty operate within a fixed total envelope. Every possible experience on the ship is a variant on a small number of basic categories. There is no horizon you have not yet walked to. There is no person you might meet who came from somewhere you have never been. There is no weather, no season, no chance encounter with something genuinely unexpected that the ship's designers did not anticipate and arrange. The psychological literature on confinement suggests that people adapt to reduced novelty, that baseline expectations adjust, that meaning can be found in small variations that would be invisible in richer environments. This is true, and it is part of what makes the generation ship not psychologically impossible in principle. But adaptation has limits, and adaptation to reduced novelty comes at a cost, a lowering of the ceiling of psychological engagement, a narrowing of the range of experience that produces genuine stimulation. Over generations, this lowering of the ceiling may produce cultural effects that are difficult to predict. Cultures that develop in environments of radical constraint tend to become deeply conservative, intensely focused on maintaining the familiar, resistant to change, organized around the management of scarcity rather than the exploration of possibility. This is not irrational in the context of a generation ship, where stability is genuinely necessary and where change to critical systems can be lethal. But it may also produce a cultural stagnation that makes the crew progressively less capable of creative problem solving, exactly the capacity they will need most when something unprecedented goes wrong. Let us now talk about conflict resolution, about what happens when serious disputes arise on a generation ship, and why the absence of exit makes conflict qualitatively different from anything in ordinary human social experience. On Earth, social conflict has a powerful natural resolution mechanism that operates even when formal institutions fail. People can leave. They can remove themselves from an intolerable situation, leave the job, move from the neighborhood, end the relationship, emigrate to a different country. The possibility of exit disciplines behavior. People who make themselves intolerable to others face the consequence that others will leave, and exit provides an escape valve for conflicts that cannot be resolved, allowing the parties to separate rather than requiring resolution. On a generation ship, exit is not available. There is nowhere to go. The person you cannot stand is also present at every meal, in every common space, in every emergency, for the rest of your life and theirs. The social dynamics this creates are not well studied in humans, because humans have always had the option of exit to one degree or another, even in the most constrained historical situations. The closest analogues are long-duration prison sentences and life in extreme religious communities, where departure is socially catastrophic. The prison literature documents the psychological adaptation to total confinement, the development of elaborate social hierarchies and informal governance systems, the emergence of intense loyalty structures and equally intense enmity structures, the psychological significance of small territories and minor privileges in the absence of any larger freedoms. These adaptations are real and sophisticated. They also involve a level of psychological damage that no one would choose as a model for healthy community life. Religious communities offer a more functional model, the Hutterites, certain monastic traditions, where commitment to a shared belief system and shared life creates genuine community in highly constrained circumstances. But these communities have chosen their confinement. They have exit available, even if exit is socially costly. They have contact with the outside world. They recruit new members. The constraints that sustain their community are chosen rather than imposed. A generationship community that loses the voluntary character of its confinement, when the second and later generations did not choose, and that has no contact with the outside world and no possibility of recruiting new members, exists in a condition of constraint that has no precise historical parallel. The social dynamics of that condition cannot be reliably predicted from any existing model. What can be said is that conflict resolution mechanisms will be tested severely. Disputes that would be resolved by separation in an open society must instead be resolved or managed within the closed system. The capacity for forgiveness, compromise, and sustained cooperation with people who have genuinely wronged you, and the institutional frameworks that make this sustainable, will be among the most critical capacities a generationship community can develop. Designing those frameworks before departure, when there is still time to think carefully, consult widely, and draw on the full range of human political and social wisdom, is one of the most important preparations a generationship mission can make. And it is probably among the least discussed. Let us now talk about language in more depth, specifically about the mechanisms by which language change on a generation ship could create practical barriers to technical knowledge transmission that no one predicted. When the ship departs, its technical documentation is written in the language of the founding generation. Every maintenance manual, every engineering specification, every medical protocol, every navigational procedure, all in the language of departure. Over generations, as the ship's spoken language evolves in isolation, the gap between the archival technical language and the living spoken language grows. This is not a hypothetical. It is the documented history of every language in every isolated community. The English of Shakespeare, 4 centuries removed, requires substantial study for modern English speakers. The English of Chaucer, 6 centuries, is borderline inaccessible without dedicated training. Old English, 1,000 years, is a different language in all practical respects. A generation ship on a 430-year voyage to Proxima Centauri would experience roughly the same temporal distance from its founding language as Chaucer is from contemporary English, except under conditions of extreme isolation that accelerate linguistic change rather than the mass media and standardized education that slow it on Earth. At the end of the voyage, the technical documentation written by the founding generation may require specialist training to interpret correctly. The maintenance manual for the propulsion system may be in a language that the arriving crew's engineers can only partially read. The medical protocols for managing radiation illness may be in a register that bears the same relationship to the crew's spoken language that Chaucer's English bears to modern English. This is a solvable problem in principle, maintaining a stable archival language for technical purposes, analogous to the role of Latin in medieval European scholarship or classical Arabic in Islamic scholarship, is possible if the educational system explicitly teaches it, and if there is sufficient cultural value placed on technical literacy in the archival language to motivate that teaching. But maintaining that educational system and that cultural value across 4 centuries of isolation and cultural evolution requires exactly the kind of sustained institutional commitment that is difficult to guarantee. If the archival technical language is not used in daily life, if it is reserved entirely for technical documentation, it becomes progressively more alien to daily speakers, and the effort required to maintain functional reading competency in it becomes progressively greater. In an environment of limited resources and competing demands on attention, that effort may not always be sustained. The specific failure mode to fear is not that anyone decides to abandon the archival language, but that the transmission weakens incrementally, each generation teaching it a little less thoroughly, maintaining functional competency in slightly fewer people, until, at some point, there are not enough people who can reliably read critical technical documents to handle a major engineering crisis. Let us now talk about what happens in the final approach to the destination, about the specific challenges the ship faces when it begins to transition from a voyage to an arrival. After centuries in transit, the ship approaches the target star system. The people aboard have known nothing but the ship their entire lives. Their skills, their knowledge, their psychological adaptations, their physical conditioning, all developed in the context of the ship's closed environment. They are about to confront something for which nothing in their experience has prepared them. The target system presents a set of unknowns that Earth-based observations can characterize only partially. The planet that appeared from 4.24 light-years to have potentially habitable conditions may prove, on close approach, to be marginally unsuitable in ways that change everything. The atmosphere may contain compounds that Earth's telescopes could not detect, but that are toxic. The local biology, if there is any, may present threats or complications that no one predicted. The geology may be unstable in ways inconsistent with surface settlement. The arriving crew must assess all of this from the ship, conducting detailed reconnaissance before committing to any surface operations. This requires scientific competencies that have been maintained across the voyage: planetary science, atmospheric chemistry, geology, biology if relevant. The crew that arrives must be capable of genuine scientific assessment, not just execution of pre-designed protocols, because the protocols designed at departure were based on information that is 4 light-years old and decades out of date. After assessment, if the destination is viable, the transition from ship dwelling to surface dwelling begins. This is itself an enormous challenge. The ship's crew has been adapted for ship conditions, specific gravity, specific air quality, specific psychological environment. Moving to a planetary surface means adapting to conditions that may differ from ship conditions in multiple simultaneous ways. Different gravity, different atmospheric composition, different light spectra, different microbial environment, different thermal cycles. The physical adaptation may be painful and slow. People whose musculoskeletal systems developed in the ship's gravity, which may have been managed at a slightly sub-Earth level for engineering reasons, will feel Earth-like gravity as abnormally heavy. Their cardiovascular systems, calibrated to the ship's environment, will need to adjust. Their immune systems, adapted to the ship's specific microbiome, will encounter an entirely new one. The psychological adaptation may be even more disorienting. Open skies after a lifetime of enclosed spaces. Horizons after a lifetime of walls. Weather after a lifetime of climate control. The full sensory complexity of an alien natural environment, sounds, smells, textures, visual complexity that no cultural preparation could fully anticipate. Some crew members may find this overwhelming rather than liberating. The psychological response to sudden environmental richness after lifetime deprivation is not well characterized. And all of this must happen while the crew is also establishing the basic infrastructure of the colony: shelter, food production, power generation, medical facilities, in an environment that does not yet have any of these things. The founding work of a new civilization, performed by people who are simultaneously adapting to a radically new physical and sensory environment with no external support, on the basis of technical knowledge that has been transmitted across centuries in a closed system. This is the moment the entire enterprise has been building toward, and it is, in many ways, the hardest part. Let us now talk about the relationship between the generation ship concept and the broader question of why humanity might attempt interstellar travel at all, about what the stakes are and whether they justify the costs. The most commonly cited justification for interstellar expansion is civilizational insurance. Earth faces genuine long-term existential risks. Asteroid and comet impacts capable of mass extinction, supervolcanic eruptions, the eventual fate of the Sun, and more proximate human-caused risks, including nuclear war and other civilizational catastrophes. A civilization confined to a single planet is a civilization whose entire history can be ended by a single, sufficiently large disaster. Expansion to other star systems, in this view, is ultimately necessary for the survival of intelligence over cosmic timescales. This argument is logically coherent, but involves a tension that its proponents do not always acknowledge. The people who will bear the costs of the first-generation ships, the crew members who will spend their lives in confined interstellar transit, and especially the generations born aboard who never chose their situation, are paying a real price now for a benefit that accrues to others in the distant future. Whether it is ethical to impose that price is a genuine question, not a rhetorical one. The counter-argument is that all human societies impose costs on individuals for collective benefit, through taxation, through military service, through the constraints of living under law, and that the generation ship is an extreme version of this universal dynamic, rather than something categorically different. The crew members who choose to go are choosing as individuals. The children born aboard inherit a situation they did not choose, but so does every human born into any social circumstance they did not choose. This counter-argument is not obviously wrong, but it also does not fully dissolve the ethical concern. The children born on a generation ship face constraints qualitatively more severe than the constraints imposed by ordinary social circumstances. They cannot exit, they cannot choose differently, they cannot even access the full range of human experience that would allow them to understand what they are missing. Whether this is compatible with a meaningful conception of human autonomy and dignity is a question that deserves to be taken seriously rather than dismissed. The honest position is probably that the ethical questions around the generation ship do not have clean answers, that reasonable people holding common values can reach different conclusions, and that any serious program to build and launch generation ships should grapple with these questions explicitly rather than treating them as already resolved. Let us now talk about what a realistic research agenda would look like for someone who wants to actually improve the prospects of a generation ship, about what specific questions need answering and what kinds of work would answer them. The genetic viability question needs better quantitative modelling than it currently has. The existing models make simplifying assumptions about mating patterns, migration, and bottleneck probabilities that limit their reliability. Better models would incorporate realistic social dynamics, would explicitly model the effect of different governance approaches to genetic management, and would integrate the potential contribution of frozen genetic material to the functional gene pool. This is tractable computational biology, and it would significantly sharpen our understanding of the minimum viable population question. The closed life support system question needs long-duration empirical testing. Biosphere 2 was the right idea, executed under-resourced and before the relevant engineering knowledge was adequate. A new generation of closed system experiments, smaller in scope but more rigorously controlled, focused on specific subsystem performance over multi-year periods, would generate the empirical data needed to design reliable generation ship life support. These experiments would also be directly relevant to Earth applications in controlled agriculture, waste treatment, and resource cycling. The psychological sustainability question needs data from longer isolation studies than currently exist. The Mars 500 study was 520 days. Studies of 2, 5, or 10 years with diverse participant populations in environments designed to be more representative of actual generation ship conditions than the Moscow simulation module would substantially extend the empirical base for understanding long-duration isolation effects. These studies would be ethically complex, but not ethically impossible, and the data they would generate would be invaluable. The knowledge transmission question needs empirical research on how technical competence degrades across generations in isolated communities. This could be approached through historical case studies of isolated technical communities, through designed experiments in which groups attempt to maintain technical knowledge across simulated generational transitions, and through analysis of how existing long-lived technical institutions maintain competency over time. The goal would be to develop principles of knowledge system design that maximize transmission reliability. The governance question needs work from political science, organizational theory, and legal scholarship. The specific challenge, designing institutions that remain legitimate and functional across multiple generations in closed, high-stakes environments, is novel but not unrelated to existing scholarship on constitutional design, long-lived organizations, and the governance of common pool resources. Building a research program at the intersection of these fields, focused specifically on the generation ship problem, would produce both academic insights and practical design principles. None of this research is exotic. All of it is doable with current methods and resources. What is lacking is not capability, but a research community explicitly organized around these questions and sustained by sufficient funding to pursue them seriously over the decades required. The generation ship is probably centuries away from being feasible. That is exactly why the research should begin now, because the questions are hard enough that even centuries of work may not fully answer them, and because some of the most important preliminary research, like long-duration closed ecosystem studies, requires decades of observation to yield useful data. The generation ship concept does not need more enthusiastic speculation. It needs more rigorous science. Let us now talk about what all of this implies for our understanding of the Fermi paradox, about what the generation ship problem suggests about the prevalence of technological civilizations in the galaxy, and why intelligent life might be rarer than the optimistic Drake equation estimates suggest. The Fermi paradox asks a simple question. If intelligent life is common in the galaxy, and if technological civilizations eventually develop the ability to expand beyond their home star systems, where is everybody? The galaxy is 13 billion years old. Even at sublight speeds, a civilization that began expanding 1 billion years ago could have reached every star in the galaxy by now. And yet, we see no signs of any other civilization anywhere. One class of explanations for this silence involves what is sometimes called the Great Filter, some barrier that most evolutionary pathways fail to cross either before or after the emergence of intelligent life. The generation ship problem, and more broadly, the problem of maintaining a viable technological civilization over the timescales required for interstellar expansion, could be part of this filter. Consider what a civilization must sustain to successfully expand to other star systems. It must survive long enough to develop the required technology, at minimum centuries, probably millennia, of uninterrupted technological progress. It must avoid civilizational collapse from war, ecological catastrophe, or other self-inflicted damage long enough to build and launch interstellar missions. It must successfully sustain crews across multi-century voyages, and it must establish viable colonies at the destination. Each of these requirements is a filter. Most evolutionary pathways that produce intelligence may fail to navigate all of them. Civilizations that develop the technology for interstellar travel may destroy themselves before building the ships. Civilizations that build the ships may lose them to the compounding risks of multi-generational voyages. Civilizations that arrive at their destinations may fail to establish viable colonies. The generation ship problem, seen through the Fermi paradox lens, is not just an engineering challenge for our own civilization. It may be a representative challenge for all technological civilizations, a consistent barrier to interstellar expansion that explains, at least in part, why the galaxy appears empty rather than full of civilization. This does not mean expansion is impossible. It means it is hard in ways that may be consistently hard across different biologies and different histories. The same problems we face, maintaining genetic diversity in small, isolated populations, sustaining psychological health in confined environments, preserving technical knowledge across generations, may face any civilization attempting interstellar expansion, regardless of the specific biological or technological details. If this is right, then solving the generation ship problem is not just a practical challenge for our own civilization's future. It is a contribution to understanding why the galaxy looks the way it does, and potentially a key to changing what it looks like over the next billion years. Let us now talk about the specific question that underlies all of this, about what the generation ship problem reveals about the nature of human civilization, and whether civilization as we know it is the kind of thing that can survive in a bottle. Our civilization is not a self-contained object. It is a process, a continuous, globally distributed, massively interconnected process of knowledge generation, transmission, application, and critique that depends at every point on the contributions of billions of individuals, the infrastructure of global trade and communication, the accumulated institutional wisdom of thousands of years, and the constant creative friction of diverse traditions encountering each other. The generation ship puts a tiny fragment of this process in a bottle and asks it to sustain itself. Not just to sustain the physical conditions for human survival, to sustain the intellectual, cultural, and social conditions for something recognizable as civilization. For the thing that makes the generation ship mission possible to still be possible when the ship arrives, for the arriving crew to be capable of the creativity, technical competence, and social organization required to establish a new civilization, the process of civilization must have been sustained within that bottle across the entire voyage. Whether that is possible, whether a fragment of civilization can sustain itself without the connections that normally sustain it, is the deepest question the generation ship poses. Not about physics, not about engineering, about the nature of the thing we are trying to carry. The honest answer is that we do not know. We have never tried, and we will not know until someone does. Let us talk about something that is almost never discussed in generation ship literature: the problem of what happens to the people who are left behind. When a generation ship departs, it takes thousands of people with it. These are not random people. They are selected for specific qualities. They are likely among the most technically competent members of their civilization, the most psychologically resilient, the most physically healthy, the most socially cooperative. They represent a significant concentration of human capability, assembled at enormous cost, and then removed from Earth permanently. The civilization that built and launched the ship bears this cost. It invests decades or centuries of resources in the mission, the engineering, the construction, the training, the launch infrastructure, and then it sends those resources away forever. The people who go do not come back. The knowledge they carry does not return. The investment produces no economic return, no technological transfer, no direct benefit to the civilization that made it. This is a profoundly unusual structure for a major investment. Most large human enterprises, dams, cathedrals, research programs, produce benefits for the society that funded them. The generation ship produces benefits, if it produces them at all, for a society that does not yet exist, at a star system that current civilization will never interact with in any practical sense. The communication delay alone, more than 4 years one way to Proxima Centauri, ensures that whatever the colony establishes will never be directly integrated with Earth civilization. Whether any human civilization will sustain the motivation to make this investment, and to make it repeatedly across the decades or centuries required to launch multiple missions, is deeply uncertain. The political economy of large, long-duration projects is challenging even when the benefits are clear and domestic. Projects that require sustained commitment across multiple political cycles, whose benefits accrue to future generations rather than current constituencies, whose costs are concentrated and immediate, while their benefits are diffuse and distant. These are exactly the kind of projects that democracies and market economies struggle to sustain. The history of large science infrastructure provides some relevant examples. The Apollo program was sustained for roughly a decade before political priorities shifted. The superconducting Super Collider was cancelled mid-construction in 1993 after more than $2 billion had been spent, because Congress lost confidence in the project. ITER, the International Fusion Experiment, has been in development for decades and has faced repeated delays and budget overruns, driven partly by the difficulty of sustaining international commitment across changing political landscapes. A generation ship program would make all of these look modest. The development timeline would be measured in decades at minimum, probably centuries. The cost would dwarf any previous human undertaking. The benefits would not materialize within any political cycle, within any human lifetime, within any generational span that creates normal political accountability. What kind of institutional structure could sustain this? Not a democracy with 4-year election cycles. Not a market economy responding to quarterly earnings. Some kind of long-duration institution, a foundation, a religious organization, an international consortium with extraordinary stability, would need to maintain commitment across whatever timeframe development requires. Whether such an institution can be created and sustained in a world with the normal dynamics of political change and economic volatility is itself a deep uncertainty. The generation ship may face a governance problem not just aboard the ship, but in the civilization that builds it. Let us now talk about the specific question of terraforming and planetary engineering, about whether the destination, even if potentially habitable, might require active modification before human settlement becomes viable, and what this implies for the arriving crew's capabilities. The The most optimistic generation ship scenarios assume the destination has a planet in the habitable zone with liquid water, a breathable atmosphere, and conditions compatible with direct human settlement. This is a specific and not particularly likely set of conditions. The range of planetary environments consistent with hosting liquid water is significantly broader than the range compatible with direct human habitation without life support equipment. A planet with the right temperature range and liquid water may still have an atmosphere with insufficient oxygen, with toxic gases, with pressure incompatible with unprotected surface activity. Its microbial biosphere, if it has one, may produce metabolic byproducts that are harmful to humans. Its soil chemistry may be incompatible with growing earth food crops. Its radiation environment, if it lacks a strong magnetic field, may require permanent surface shielding. In these scenarios, the arriving crew faces not just the challenge of establishing a colony, but the challenge of beginning planetary engineering, modifying the planet's atmosphere, its chemistry, its biological environment, over timescales that may themselves be generational. This is a form of terraforming, though perhaps more modest than the full-scale terraforming of science fiction. The question is whether the arriving crew, after centuries of transit in a closed ship with limited resources and the cumulative effects of all the stresses we have discussed, is capable of the sustained, creative, technically sophisticated work that planetary engineering requires. Whether the knowledge base transmitted across the voyage is adequate not just for maintaining ship systems, but for the active modification of a planetary environment. This requires capabilities that go beyond maintenance. It requires the capacity for genuine scientific research, for engineering innovation, for the development of new techniques in response to conditions that no one fully anticipated. These are precisely the capabilities most vulnerable to the cultural stagnation and knowledge degradation risks that make the generation ship so difficult. A crew that arrives technically competent but culturally conservative, adapted to the stability prioritizing culture of the ship, skilled at maintaining known systems but less skilled at developing new ones, may find planetary engineering deeply challenging. The transition from maintenance mode to innovation mode is not automatic and may require exactly the kind of cognitive flexibility that long-duration confinement tends to reduce. Let us now talk about the specific challenge of maintaining scientific knowledge aboard a generation ship. Not just technical knowledge for maintenance purposes, but the capacity for genuine scientific inquiry that the mission may require. Science is not just a body of knowledge, it is a method, a specific set of practices for generating reliable knowledge about the world through observation, hypothesis formation, experimental testing, and peer critique. This method requires institutional support, the tradition of published literature providing context for new work, the community of practitioners who evaluate and challenge each other's findings, the material infrastructure of laboratories and instruments, and the culture of skepticism and openness to revision that makes science self-correcting. Most of these conditions are difficult to maintain on a generation ship. The published literature can be carried digitally, but it cannot be updated with new work from Earth once communication delays become prohibitive. The community of practitioners is limited to whoever is aboard, too small for the kind of diverse peer critique that makes science robust. The laboratory infrastructure is whatever the ship can carry, with no possibility of acquiring new instruments or materials. The culture of scientific skepticism must be actively maintained against the conservative pressures of isolated community life. In practice, science aboard a generation ship would probably function differently from science on Earth, more like the natural philosophy of an earlier era in which a small number of generalist scholars worked with limited instruments across multiple domains, than like the specialized, institutionally elaborate science of the present. This is not necessarily a failure. Important science has been done by individuals and small groups with modest resources, but it represents a significant downscaling of scientific capacity relative to what the civilization that built the ship could achieve. The specific scientific capabilities most critical for the mission are those required for maintenance and adaptation: materials science, biology, medicine, engineering, environmental science. These are the domains where knowledge gaps are most immediately dangerous. Basic physics and mathematics, once transmitted, are unlikely to be lost. They are too fundamental and too self-consistent to degrade. But applied knowledge in complex domains, where successful application requires not just theory, but extensive practical experience, this is where the transmission gaps are most likely. The medical knowledge problem is particularly serious. Modern medicine depends on a vast infrastructure of specialized training, diagnostic technology, pharmaceutical manufacturing, and continuing research. A generation ship can carry some of this: medical personnel with substantial training, diagnostic equipment, a pharmacy adequate for anticipated needs. But medicine evolves, and diseases evolve, and the ability to respond to unanticipated medical challenges requires research capabilities that a generation ship can support only in limited form. A novel pathogen, a mutation of an existing shipboard microorganism that begins causing disease in ways the existing pharmacopoeia cannot address, requires exactly the kind of rapid scientific response that a generation ship is least equipped to provide. The research, development and testing of a new treatment under conditions of limited laboratory infrastructure and limited pharmaceutical manufacturing capability may take years, during which the pathogen continues spreading through the closed population. Let us now talk about something more fundamental, about what the generation ship reveals when we look at it not as an engineering challenge, but as an anthropological one. Anthropology, the study of human beings and human societies, has documented the remarkable diversity of ways that humans have organized their lives, their communities, their relationships to time and space and meaning. Every culture that has been studied, however different from every other, shares certain universal features: kinship systems, ritual, narrative, a sense of sacred and profane, systems for transmitting knowledge across generations, mechanisms for managing conflict, and some framework for answering the question of what makes a human life meaningful. These universals are not accidents. They are solutions to universal problems that every human community faces: how to organize reproduction and child-rearing, how to coordinate collective action, how to manage the emotional complexity of human social life, how to transmit what one generation knows to the next. They have been independently developed, in somewhat different forms, by every human community in history. The generation ship is a new kind of human community, one facing all the universal problems of community life under conditions more extreme than any human community has previously faced. It will develop its own solutions to these universal problems. Those solutions will not be identical to any existing human culture. They will be shaped by the specific conditions of the ship: the confinement, the closed resources, the mission, the absence of exit, the knowledge that survival requires technical competence across generations. What those solutions will look like, what the culture of a generation ship will actually be, cannot be designed in advance in any detail. Culture is an emergent property of communities, living through specific conditions over time. The founding generation can shape the conditions, can establish initial institutions and norms and values, can try to create the cultural substrate from which a viable, long-duration culture might grow, but it cannot specify the culture itself. This is perhaps the deepest uncertainty in the generation ship problem. Not whether the life support systems will work, not whether the genetics will hold, not whether the governance will sustain, but whether the culture that emerges from the specific conditions of interstellar confinement will be one that can sustain human well-being, maintain technical competence, and deliver a viable community to the destination. History suggests that humans are remarkably adaptable, that communities have survived and sometimes flourished under conditions of extreme constraint. History also suggests that isolation and extreme constraint produce cultural forms that look bizarre or troubling from the outside, that the solutions communities develop to the problems of survival under extreme conditions are not always solutions that produce psychological health or human dignity. The generation ship will produce a culture. Whether that culture is one that we would want to have produced, whether the humans who arrive at Proxima Centauri after 4 centuries of interstellar transit are humans whose lives, and the lives of all the generations between them and the founders, were well lived by any reasonable standard, this is the question that engineering and physics and biology cannot answer. It is a question about values, about what we think human life is for, about whether the expansion of civilization to other stars is worth the cost that the people who pay it, not the civilizations that benefit, but the specific individuals who live and die on the ship, actually bear. Let us now talk about a possibility that is rarely discussed in generation ship literature, but that deserves serious consideration. The possibility that the generation ship crew, having lived through the voyage, might decide on arrival not to establish the colony as planned. They have arrived. They have achieved what their ancestors set out to achieve. They stand at the edge of a new star system after centuries of transit, with the full weight of the voyage behind them and the full openness of the destination before them. And they might decide, no. Not because the planet is uninhabitable, not because the systems have failed, but because they are people with their own values and their own understanding of what they want, and what they want may not be what the founding generation intended. The founding generation wanted to establish a colony. They designed the ship for this purpose. They selected crew members who expressed commitment to this purpose. They built institutions designed to transmit this purpose across generations. But transmission is imperfect, and values evolve. The 14th generation may understand the mission differently than the founders did. They may place different weight on the costs and benefits. They may have developed philosophical or religious frameworks that lead them to different conclusions about the right relationship between humans and unexplored worlds. They might choose to remain in orbit and observe, to study the destination system without colonizing it, treating the system as something to be understood rather than settled. They might choose to return to Earth, a journey of equal length, rather than commit to a surface colony for which they feel insufficient enthusiasm. They might choose to continue outward, to not settle here, but to keep going, treating the voyage itself as their civilization, rather than settlement as its goal. These choices seem improbable from the perspective of the founding generation, but across 4 centuries of cultural evolution in isolation, the values of the arriving crew are genuinely uncertain. The mission they feel themselves to be on may not be identical to the mission on which their ancestors embarked. This is not a failure of the generation ship concept. It is a feature of carrying not just human bodies, but human autonomy across interstellar distances. A ship full of people will arrive as people, with their own judgments, their own values, their own understanding of what is right. The founding generation can shape those values and judgments through the cultural systems they establish. They cannot determine them. Whether this is reassuring or troubling depends on what you value more, the success of the mission as conceived by the founders, or the autonomy of the people who actually make the journey. Let us now talk about the concept of the seed ship, the alternative to the generation ship that avoids the human dimension entirely, by carrying not people, but the biological and informational substrates from which people could be grown at the destination. A seed ship carries no living crew. It carries frozen embryos or frozen gametes, or, in the most radical version, only digital sequences representing human DNA, along with the automated systems required to actualize those sequences into living human beings and raise the resulting children to adulthood at the destination. This approach eliminates the generation ship's most difficult problems: no multi-generational psychology, no cultural drift, no knowledge transmission failures across human generations, no governance crises, no social conflict in the confined space of a ship. The ship itself is a cargo vessel, sophisticated cargo, but cargo, rather than a civilization in transit. The problems it introduces are different in kind. Growing a human embryo to term requires either a biological uterus or an artificial one. Artificial uterine technology, the ability to gestate a human fetus entirely outside a biological mother from embryo to term, does not currently exist in any form approaching reliability. The research that would be required to develop it is ethically constrained by the obvious implications of working toward a technology for growing human beings outside their biological mothers. Implications that touch deep cultural, religious, and ethical sensitivities across many human traditions. Raising children to adulthood without human parents requires substitutes for the specific developmental inputs that parental care provides: the emotional attunement, the responsive relationship, the thousands of daily interactions through which children develop the psychological and social capacities required for human life. Whether AI systems can provide adequate substitutes is genuinely unknown. The developmental psychology literature identifies parental responsiveness and emotional connection as among the most critical inputs to healthy child development. Whether a sufficiently sophisticated AI system could provide equivalent inputs at the level of emotional authenticity, responsiveness, and developmental appropriateness required has no empirical answer. And even if the technical problems of gestation and early childhood care were solved, the education problem remains. The children grown at the destination must know enough to establish a colony. They must have the technical knowledge required to maintain the ship's systems during the transition period before the colony is self-sufficient. They must have the social knowledge required to function as a community. They must have the historical and cultural knowledge required to understand what they are and where they came from. All of this must be provided by systems: AI, recorded human material, curriculum, without the living cultural transmission that normally embeds knowledge in lived practice. A colony of children raised by machines at an alien star, with no living memory of Earth and no human adults who knew the founding generation. This is a genuinely strange vision of human civilization. Not impossible in principle, but strange in ways that deserve serious ethical and cultural reflection before being adopted as a plan. Let us now talk about what it would actually feel like to make the decision, the specific moment when a civilization commits to launching the first-generation ship, knowing everything we have discussed. This would not be a simple technological milestone, like a rocket launch or a new particle physics result. It would be one of the most morally weighted decisions a civilization has ever made. The people who make it know what they are committing to, not just the engineering costs, not just the financial costs, but the human costs. They are committing to putting thousands of people in a closed vessel that will not arrive at its destination within any of their lifetimes. They are committing to creating conditions in which thousands of people who will be born aboard and will never choose this, will live their entire lives in radical confinement at elevated radiation risk, with elevated cancer rates, without open skies, without the possibility of exit, in service of a mission they did not choose. They are doing this knowing that the mission may fail, that any of the multiple failure modes we have discussed may materialize, that the ship may arrive in a state too compromised to establish a viable colony, or may not arrive at all. They are doing this because they believe the benefit is worth the cost. Because they believe that the long-term survival of intelligence in the universe requires expansion beyond a single planet, and that the costs borne by the individuals who make that expansion possible are justified by the stakes. Because they believe that the people who go, and the people who are born aboard, will find their lives meaningful despite the constraints, that the voyage itself will produce a human experience that is genuinely valuable, not just instrumentally, but in itself. Whether this belief is justified, whether the generation ship is a form of collective heroism or a form of collective imposition, is not a question with an obvious answer. It is the kind of question that a civilization should sit with carefully before acting on it. It is also, in a real sense, the most important question the generation ship poses. More important than the engineering, more important than the genetics or the psychology or the governance. Because if the answer is that the costs are unjustifiable, that no benefit to distant future generations can justify the specific constraints imposed on the specific individuals who live and die between the stars, then none of the engineering matters. And if the answer is that the costs are justifiable, that this is what civilizational courage looks like, that this is what it means to take responsibility for the long-term future of intelligence, then all of the engineering matters enormously, because getting it right is how you minimize the costs borne by the people who pay them. There is no dodging this question. The generation ship raises it with unusual clarity. Every generation ship mission, if such missions are ever launched, will be built on someone's answer to it. The answer a civilization gives to this question says something profound about what kind of civilization it is, about what it values, about how it relates to future generations, and to the individuals who bear the cost of serving them, about whether its ambitions are worthy of the name. Let us talk about the specific problem of ship size, about what the physical dimensions of a viable generation ship actually imply, and why the numbers that come out of realistic analysis tend to be significantly larger than popular treatments of the concept suggest. Start with population. We have established that the minimum viable founding population for a multi-century voyage is probably several thousand people. Let us use 2,000 as a conservative working number, accepting that this is probably an underestimate for longer journeys. 2,000 people require living space, not just sleeping space, the kind of space required for psychological health across lifetimes. For comparison, the most space-efficient permanent human habitation environments that have been studied carefully suggest roughly 25 to 35 square meters of total living and working space per person as a practical minimum for long-duration health. Below this, measurable psychological degradation accelerates. At 30 square meters per person for 2,000 people, habitation alone requires 60,000 square meters, 6 hectares of floor space. This is before agricultural area. A closed food production system for 2,000 people requires roughly 1 to 2 hectares of productive growing area per person under optimistic assumptions about agricultural yield in controlled environments. Call it conservatively half a hectare per person, or 1,000 hectares total for a minimally adequate food system. This is almost certainly an underestimate, because closed system agriculture has never been demonstrated at this yield efficiency over multi-decade periods. Even at a fraction of this agricultural area, If synthetic food production or other high-efficiency systems reduce the required growing area by 90%, the agricultural footprint alone exceeds the habitation footprint by a significant margin. Add the mechanical systems, propulsion, power generation, fuel storage, life support equipment, medical facilities, manufacturing capability, water and air recycling systems, redundant backups for all critical systems. The mass of these systems, which determines the energy required to accelerate them to interstellar speeds, dwarfs the mass of the people they support. A realistic generation ship mass estimate, when all of these requirements are integrated, comes out somewhere in the range of millions to tens of millions of metric tons. For comparison, the entire mass of the International Space Station is approximately 420 metric tons. The largest ship ever built, the Seawise giant supertanker, was approximately 660,000 metric tons fully loaded. A generation ship for 2,000 people is likely 10 to 100 times the mass of the largest ship ever built by human civilization. And it must be accelerated to a significant fraction of the speed of light. The energy required to accelerate 10 million metric tons to 1% of the speed of light is approximately 4.5 times 10 to the 22nd power joules, roughly 10,000 times the current annual energy consumption of all human civilization. And this energy must be carried as fuel aboard the ship, or beamed from an external source. There are no refueling stations in interstellar space. These numbers do not make the generation ship impossible. They do place it firmly in the category of civilizational scale projects rather than national scale ones. The Apollo program, the largest coordinated engineering effort in human history, cost approximately $150 billion in today's dollars and required a workforce of 400,000 people at its peak. A generation ship program would require resources and coordination several orders of magnitude beyond this, sustained over decades or centuries rather than years. This has implications that go beyond the obvious question of cost. A project of this scale requires a civilization of correspondingly large scale to undertake it, one with sufficient economic surplus, institutional stability, and coordinating capacity to sustain the effort across the necessary time frame. It requires not just resources, but the political and cultural will to allocate those resources to a purpose whose benefits are centuries or millennia away. Whether any version of human civilization as it currently exists, or as it is likely to exist in the foreseeable future, can sustain this, is genuinely uncertain. Let us now talk about the specific question of propulsion more carefully, about the realistic options for moving a generation ship at interstellar speeds, and what each implies for the overall mission design. Chemical propulsion, the technology we currently use for all space missions, is completely inadequate for interstellar distances. The most energetically efficient chemical reaction available produces exhaust velocities of approximately 4.5 kilometers per second. Accelerating any significant payload to even a fraction of a percent of the speed of light using chemical propulsion would require a fuel-to-payload mass ratio so extreme as to be physically impossible within any reasonable constraint on total ship mass. Nuclear thermal propulsion, heating a propellant by passing it through a nuclear reactor, improves on chemical rockets by roughly a factor of 2 in exhaust velocity. This is useful for inner solar system missions, but still completely inadequate for interstellar travel. The improvement is real, but the scale of the problem is too large. Nuclear pulse propulsion, the Orion concept, involves detonating nuclear devices behind the ship and riding the pressure wave. This can, in principle, achieve exhaust velocities of tens to hundreds of kilometers per second, making it potentially usable for interstellar travel on timescales of centuries rather than millennia. The concept was seriously studied in the 1950s and 1960s. The physics is sound, and the engineering, while formidable, has no obvious impossibilities. The political obstacle, achieving interstellar speeds, requires detonating thousands of nuclear devices, which is prohibited by the Partial Test Ban Treaty and its successors, is at least as significant as the engineering challenges. Nuclear fusion propulsion, using controlled fusion reactions as the energy source, would be significantly more capable than nuclear pulse if the energy could be efficiently converted to propellant exhaust velocity. Fusion fuel, deuterium and helium-3 or deuterium and tritium, is energy dense, and the exhaust velocities achievable with fusion reactions are in principle adequate for interstellar travel on century timescales at acceptable mass ratios. The problem is that controlled fusion has been 30 years away for 70 years. It remains the most promising but most elusive energy technology in human development. Antimatter propulsion, using matter-antimatter annihilation as the energy source, would be the most capable option physically, with exhaust velocities approaching the speed of light. The energy density of antimatter is orders of magnitude beyond any other fuel. The problems are severe. Antimatter does not occur naturally in useful quantities. Producing it requires enormous energy inputs. Storing it requires magnetic containment systems that do not exist at scale, and the infrastructure required to produce enough antimatter for an interstellar mission is itself a civilizational scale undertaking beyond the generation ship itself. Laser sails, using a powerful ground-based or space-based laser to push a reflective sail, offer an alternative to onboard propulsion. The Breakthrough Starship initiative has proposed using arrays of high-power lasers to accelerate small probes to 20% of the speed of light. For probes massing a few grams, this may be achievable, with technology not dramatically beyond what exists today. For a generation ship massing millions of metric tons, the required laser power scales accordingly. It becomes a laser array of effectively planetary scale, requiring energy inputs that strain any realistic infrastructure estimate. None of these options is currently available for a generation ship mission. Each represents a specific technological development program, some more plausible in the near term, some requiring breakthroughs in physics or engineering whose timeline is genuinely uncertain. The propulsion problem is the most technically clear-cut of the generation ship's challenges, in the sense that the physics is well understood and the engineering requirements are calculable. But the scale of those requirements, and the uncertainty about when or whether the required technologies will mature, means that propulsion remains a genuine obstacle rather than a solved problem. Let us now talk about the interplay between propulsion capability and the human problems of the generation ship, about how the two categories of challenge interact and why solving one affects the other. If propulsion technology improves to the point where interstellar travel becomes possible at 10% of the speed of light rather than 1%, if the journey to Proxima Centauri takes 43 years rather than 430, the human problems change dramatically. A 43-year journey is within a single human lifetime. The multi-generational psychology problem disappears. The knowledge transmission problem becomes trivial. The same people who know how to maintain the ship at departure still know how to maintain it at arrival. The genetic diversity problem disappears. 43 years is not long enough for meaningful population genetic changes in any closed population. What remains at 43 years? A genuine and serious psychological challenge. 43 years of confinement in a closed vessel is extraordinarily demanding. A genuine medical challenge, radiation exposure over 43 years in the interstellar cosmic ray environment, is significant. A genuine engineering challenge, the life support systems must function reliably for 43 years without resupply. These are hard problems, but they are tractable hard problems, problems that existing research programs are making progress on, problems that differ in degree rather than in kind from the challenges of existing long-duration space missions. This means that the human problems of the generation ship are strongly dependent on the propulsion problem, that solving propulsion doesn't just solve the physics, it also transforms the human challenge from something that may be genuinely unsolvable with human nature as it is, to something that is difficult but clearly within reach. Conversely, if propulsion technology cannot be advanced beyond nuclear pulse propulsion, if the practical ceiling for interstellar travel is something like 2 to 5% of the speed of light, with journey times of 85 to 215 years, then the human problems are real, persistent, and must be addressed directly. A 215-year journey involves roughly 7 generations. Every problem we have discussed, genetics, psychology, sociology, knowledge transmission, governance, cultural continuity, is genuinely serious at that timescale. The relationship between these two problem domains, propulsion and human factors, is not fully appreciated in most generation ship literature. The tendency is to treat propulsion as the bottleneck and to assume that once propulsion is solved, the mission is feasible. But the human problems do not disappear when propulsion improves. They only disappear when propulsion improves enough to make the journey short enough that multi-generational effects become irrelevant. And the threshold for that improvement is high, probably at least 5 to 10% of the speed of light, which is significantly beyond any near-term realistic propulsion technology. Let us now talk about the specific question of what a successful generation ship mission would actually look like from the inside, about what daily life might resemble for different generations at different points in the voyage, and how the experience transforms from beginning to end. The founding generation departs with the full emotional weight of leaving Earth forever, probably the most profound single experience any human being has ever undergone. They carry with them the specific embodied memories of Earth, the smell of rain, the experience of open sky, the sensation of unmanaged weather, the presence of a vast and diverse human civilization around them. These memories are irreplaceable, unrepeatable, and will fade and distort over decades, like all human memories. In the early years of the voyage, the ship is alive with the specific energy of a new and unprecedented enterprise. Every challenge is the first of its kind. Every solution creates knowledge that did not exist before. The founding generation is doing something that has never been done, and this fact animates their experience with a quality of significance, however difficult, that is itself sustaining. By the second generation, Earth is historical rather than personal. The youngest members of the founding generation are aging. The children born aboard have never known anything other than the ship. For them, the ship is not a vessel they chose, but the world they were given. Their relationship to the mission is the relationship of inherited obligation rather than chosen purpose. Some will embrace this inheritance, others will chafe against it. The first genuine generational tension appears between those whose identity is bound up with the sacrifice of leaving Earth and those for whom the sacrifice is merely historical. By the fifth generation, the founding generation is entirely gone. Their children are old or dead. The ship has been underway for roughly 150 years at 1% of light speed. It is perhaps 1/3 of the way to Proxima Centauri. The crew alive now knows Earth only through recordings and stories and the cultural inheritance transmitted imperfectly through the intervening generations. The destination is equally abstract, a star system their grandchildren's children will reach. This generation lives entirely in the middle of something. They did not experience the departure. They will not experience the arrival. Their lives are the voyage itself, not its beginning or its end. What meaning they find must be found in the voyage, in the work of maintaining the ship, in the social life of the community, in whatever cultural and intellectual pursuits the ship affords, in the relationships and experiences of lives lived in this specific place. Whether this is enough, whether the voyage itself, lived fully and consciously, constitutes a meaningful human life, rather than an imposed waiting, is the existential question that every generation aboard must answer for itself. By the 12th or 15th generation, the destination is approaching. The star that has been a point of light gradually grows in apparent brightness. Detailed observation of the target system becomes possible, the first direct reconnaissance of what awaits. The culture that has developed across the voyage, shaped by centuries of confinement, of cultural evolution in isolation, of accumulated joys and tragedies and adaptations, faces its final transformation, from a ship culture to a colony culture, from a civilization in transit to a civilization beginning the work of establishment. Whether the people who make this final transition are ready for it, whether the culture produced by centuries of interstellar transit produces the qualities required for planetary colonization, is the ultimate test of everything the voyage has built. Let us now talk about a question that becomes more interesting the longer you think about it. Whether the generation ship, understood clearly, is actually less a transportation technology and more a new kind of civilization. Transportation technologies move people from one place to another. The ship is a means. The destination is the end. The time in transit is a cost, something to be minimized, endured, survived. But a generation ship that takes 430 years to reach its destination is not really a transportation technology in this sense. The voyage is not a cost to be minimized. It is most of the story. Dozens of generations live their entire lives aboard. The ship is not moving civilization from Earth to another star. It is creating a new civilization in the act of transit. The civilization that arrives is not the same civilization that departed. It is something new, shaped by the specific conditions of the voyage in ways that neither the founders nor the Earth they left could fully predict. This reframing changes how the success of a generation ship mission should be evaluated. If the measure of success is faithful delivery of the founding civilization's intentions to the destination, arriving with the same values, the same knowledge, the same culture that departed, then success is probably impossible. Cultural evolution over centuries of isolation guarantees that what arrives will be transformed. Judged by this standard, every generation ship will fail. But if the measure of success is the emergence of a viable human civilization at the destination, one capable of sustaining itself, of building something new, of carrying something essential of human experience forward into a new context, then the standard is different. What arrives need not be identical to what departed. It must be viable, capable, and in some meaningful sense continuous with the human tradition from which it sprang. This is not a low bar, it is a high one, but it is achievable in principle in ways that the fidelity standard is not. Understanding the generation ship as a civilization creation project rather than a transportation project changes the design priorities. You are not trying to deliver a preserved civilization across interstellar distance. You are trying to create conditions under which a new civilization can emerge from the materials of an existing one, taking the genetic diversity, the technical knowledge, the cultural foundations, and the institutional wisdom of the founding civilization, and creating an environment in which these inputs can produce something new that is also sustainable. This is what every civilization has always done with its founding moments, taken what came before and made something new from it. The generation ship makes this process visible and explicit in a way that ordinary cultural history does not. The voyage is the founding. The arrival is not the end of something, but the beginning. Let us now talk about the historical weight of what we have been discussing, about where the generation ship sits in the larger arc of human movement across the Earth, and what that history says about the impulse that would drive a civilization to attempt it. Human beings have been moving for as long as there have been human beings. The earliest populations moved out of Africa tens of thousands of years ago, walking into landscapes no human had entered before, eating foods no human had eaten before, facing weather and terrain and predators that no accumulated cultural experience had prepared them for. They moved because the capacity for movement is built into us, because the horizon is always an invitation, because the next valley might hold something the current valley does not. Every subsequent wave of human expansion into Australia and the Americas and the Pacific Islands, across the deserts and the mountain ranges, through the Arctic, has the same basic structure. People going somewhere no one from their community has gone before, with incomplete knowledge of what they will find, at significant risk of failure, because the going mattered more than the comfort of staying. The generation ship is this same impulse at the scale that our current technological moment makes visible. Not the next valley, but the next star. Not a journey of months or years, but of centuries. Not a gamble with individual lives, but with the continuity of civilization itself. What is distinctive about the generation ship is not the impulse, but the stakes. Every previous wave of human expansion involved people going somewhere that other people had already gone, or at least going to a world where the air was breathable and the food was recognizable, and the environment, however challenging, was part of the same biosphere as everything else humans had ever encountered. The generation ship goes somewhere genuinely different, to a star system that evolved independently of ours, to an environment that shares nothing with Earth's ecology, to conditions that may be subtly or dramatically incompatible with human biology, in ways that cannot be known in advance. The courage this requires, if that is what it is qualitatively different from the courage of previous expansions. Not greater necessarily. Walking into an unknown continent with stone tools required something that most contemporary humans could not summon, but different, requiring a relationship with uncertainty, with the possibility of total failure, with the certainty that you will not live to see the outcome. A relationship that is hard to sustain across the years and decades and generations required. Whether humanity will ever develop and maintain this relationship, whether the civilization of the future will be one that can look at the problem of the generation ship in all its difficulty and decide to attempt it anyway, is perhaps the question this whole discussion ultimately comes down to. It is not a scientific question. It is not an engineering question. It is a question about what kind of civilization we will be, and whether the version of us that exists when the technology becomes available will have the specific combination of humility, ambition, patience and courage that the generation ship requires? We do not know the answer. We are not yet the civilization that will answer it. We are the civilization deciding, in small ways and large, whether we move toward being that civilization or away from it. Let us talk about one specific dimension of the generation ship problem that has received almost no serious attention: the question of art, and what the ship's creative culture reveals about the broader conditions of human flourishing in radical confinement. Art is not a luxury. This is easy to say and easy to dismiss, so it is worth being specific about what the claim actually means. Art, in the broad sense that includes music, visual making, narrative, ritual, dance, and every other form of expressive human activity, performs specific psychological and social functions that are not performed by anything else. It processes experience that cannot be processed through rational analysis. It creates shared emotional states that produce social bonding. It transmits values, histories, and ways of seeing that resist propositional formulation. It provides the experience of beauty, which is not ornamental but functional, connected to the psychological states that sustain motivation and engagement with life. A generation ship without a rich and evolving artistic culture is not merely a culturally impoverished generation ship. It is a psychologically compromised one whose people lack important tools for processing the specific difficulties of their situation and for maintaining the social cohesion and individual motivation that survival requires. What does art look like on a generation ship? This is not a rhetorical question. It has specific implications for how the ship should be designed and what resources should be allocated. Music is probably the most psychologically critical art form for closed communities. It is the most social of the arts, uniquely capable of creating synchronized emotional states in groups, of producing the specific feeling of being together in a shared moment that isolated communities most urgently need. Every long-duration isolated community that has been studied has developed distinctive musical traditions, forms that reflect the specific emotional landscape of their conditions, that encode their history and values, that provide structure for collective emotional experience. On a generation ship, music will evolve. The music the founding generation brought from Earth will be transmitted, transformed, combined with new forms that emerge from the specific experience of the voyage. By the fifth generation, the music aboard will be recognizably descended from Earth traditions, but distinctively different, shaped by the acoustics of metal corridors, by the emotional landscape of perpetual confinement, by the specific joys and griefs and longings of people who have never known open sky. This musical evolution is not a problem. It is the ship's culture speaking for itself, creating the forms that its conditions require. The design implication is that the ship should allocate genuine resources to musical life, instruments adequate for the full range of musical practice, acoustic spaces designed for performance and collective listening, educational structures that transmit musical knowledge and support musical creativity across generations. Music is not decoration, it is infrastructure. Visual art on a generation ship faces a specific challenge and a specific opportunity. The challenge is that the visual environment is fixed, the same corridors, the same equipment bays, the same agricultural zones. This fixity is psychologically costly in ways we have discussed. The opportunity is that visual art, murals, sculptures, the designed character of shared spaces, can be used to create variability, meaning, and beauty within the fixed physical envelope. A ship whose visual environment evolves with its culture, whose walls tell the history of the voyage in forms that change across generations, whose spaces are shaped by the aesthetic sensibility of the people who live in them, rather than only by the engineers who built them, is a more psychologically livable ship than one whose visual environment is purely functional. Narrative is perhaps the most important art form for the generation ship's long-term cultural viability. Stories are how communities transmit their history, their values, and their sense of who they are across time. The stories a generation ship community tells about itself, about why it left, what it is doing, who its heroes are, what it is travelling toward, shape the culture's relationship to its mission in ways that governance documents and technical manuals cannot. The founding generation can tell certain stories with personal authority. What Earth was like, why they chose to come, what they hope the voyage will produce. These stories will be retold, transformed, eventually mythologized as they pass through subsequent generations. What begins as personal testimony becomes cultural narrative, becomes something approaching myth, the founding story that gives the community its identity and its sense of purpose. This mythologization is not a degradation. It is how human communities sustain meaning across time. The specific historical accuracy of the founding story matters less than the cultural work it does, whether it produces in subsequent generations a felt connection to the voyage's purpose and a sense of participating in something that extends beyond individual lives. The most successful myths are not the most historically accurate ones, but the ones that most effectively sustain the psychological and moral orientations that the community needs. A generation ship that consciously attends to its own storytelling, that makes space for the ongoing creation of narrative in forms that evolve with the community, is attending to something as essential as its water recycling systems. Let us now talk about the specific question of science fiction, about how the genre has approached the generation ship, and what serious literary treatments of the concept reveal about the problems that intuition identifies as most important. Science fiction has been thinking about generation ships for more than 80 years, and the convergence of serious treatments on specific problem areas is itself informative. The problems that keep appearing across different authors, different approaches, and different decades are probably the problems that intuition correctly identifies as most serious. Robert Heinlein's Universe from 1941, one of the earliest serious generation ship stories, identified the knowledge transmission problem as central. The inhabitants of Heinlein's ship have forgotten that they are on a ship at all. The voyage has become their entire universe, the mission has become mythology, and the technical knowledge required to complete it survives only in a persecuted minority who are regarded as heretics for claiming that the ship is moving and that a destination exists. Heinlein identified 80 years ago that the most dangerous failure mode for a generation ship is not mechanical, but cultural. That communities can lose contact with the reality of their situation in ways that make mission completion impossible. Brian Aldiss's Non-Stop from 1958, published as Starship in the United States, revisited similar territory, presenting a ship whose inhabitants have entirely lost contact with its purpose and whose society has regressed to something resembling primitive tribalism, with the ship's corridors overgrown with vegetation and its original mission entirely forgotten. Aldiss added the specific insight that regression is possible, that a technologically sophisticated community can, over generations, become less technically capable rather than more, if the conditions that sustain technical knowledge are not actively maintained. Gene Wolfe's Book of the Long Sun tetralogy, published in the 1990s, presents a ship whose inhabitants have developed a religious culture centered on the ship's computer systems, which are interpreted as gods. a specific and sophisticated treatment of the tendency for technical systems to become objects of religious reverence when they are not understood. Wolff's insight is that this transformation is not irrational given the inhabitants' situation. The computers do have extraordinary powers by the standards of the inhabitants' understanding, do respond to requests in ways that seem to reflect intentionality, and do sustain the conditions of life in ways that merit reverence, even if not the specific theological interpretation the inhabitants place on them. Kim Stanley Robinson's Aurora from 2015 is the most technically rigorous generation ship novel yet written, and the most pessimistic. Robinson researched closed ecological systems, population genetics, and the specific physics of interstellar travel extensively, and his conclusions are grim. The biology degrades, the ecosystems become unbalanced in ways that cannot be corrected, the genetic diversity narrows, and the mission ultimately fails. Not from a single catastrophic event, but from the slow accumulation of biological and ecological degradation that a closed system cannot arrest. Robinson's implicit argument is that the generation ship may not merely be difficult, but may be biologically impossible for timescales beyond a few centuries, because living systems evolved for open environments cannot be sustained in closed ones over the required timeframes. This is a serious argument, and it deserves serious engagement rather than dismissal as pessimism. Robinson is not making a philosophical claim about human spirit or institutional durability. He is making a biological claim about the dynamics of closed ecosystems. Whether he is right, whether the specific degradation dynamics he describes are inevitable or manageable, is an empirical question that requires the kind of long-duration, closed ecosystem research that does not currently exist at the required scale. What the science fiction literature collectively suggests is that the hardest problems are the ones that are hardest to quantify: the cultural drift, the knowledge loss, the biological degradation, the psychological toll of perpetual confinement, rather than the propulsion and engineering challenges that dominate most popular treatments. The stories that have been told about generation ships are more often stories about what happens to human beings inside them than stories about how to get the physics right. This convergence of literary intuition across many decades and many writers is worth taking seriously. Let us now talk about the relationship between the generation ship and the broader project of human self-understanding, about what seriously grappling with the generation ship problem reveals about who we are and what conditions our flourishing requires. Most thinking about human nature operates against a background that takes certain conditions for granted. We think about what human beings are like, what they need, what they value, but we think about this against the background of open environments, of social worlds with many thousands of potential relationships, of access to the full range of human cultural production, of the possibility of exit and change and novelty. The generation ship strips these background conditions away and asks, what is left? What is essential about human beings? What do they need at a minimum for genuine flourishing? And what is contextual, dependent on conditions that most humans take for granted, but that a generation ship cannot provide? This is not only a practical question for generation ship designers, it is one of the most profound questions in the study of human nature. The answers would illuminate not just how to build a generation ship, but what human beings fundamentally are, what the non-negotiable requirements of human flourishing look like when the negotiable ones are removed. The partial answers that emerge from the generation ship analysis suggest several things. Humans need meaningful purpose that connects to something larger than individual survival. The generation ship that fails to provide this fails psychologically, regardless of how well it is engineered. Humans need genuine social depth, not just the presence of other people, but the texture of real relationships with their complexity and development over time. Humans need some encounter with beauty, with things that are valued for their own sake rather than for their utility. And the beauty available within the confined envelope of a generationship must therefore be cultivated with the same care as its food production. Humans need the experience of genuine agency, the sense that their choices matter, that the world responds to their actions in ways that reflect their individuality. And a generationship that reduces its inhabitants to components in a system, however necessary that system is, risks producing the specific form of despair that comes from being treated as a means rather than an end. These are not new insights. They appear in different forms in every major tradition of human thought about what makes a life good. What the generation ship makes visible is that these requirements are not just philosophical ideals, but functional necessities, that communities deprived of them degrade in measurable and often irreversible ways. The generation ship thus serves, among other things, as a kind of philosophical experiment, a thought experiment made real, in which the conditions of human flourishing are tested by their removal. Let us now talk about the specific question of succession, about what happens when the founding generation begins to age and die, and the first true generational transition occurs aboard the ship. The founding generation was selected. They passed psychological screening, technical evaluations, social compatibility assessments. They were chosen from a large pool of candidates for the specific qualities that make a generation ship crew viable. They know why they are there. They chose it. The second generation was not selected. They were born. Their psychological profiles, their technical aptitudes, their social orientations were not screened for compatibility with the mission. They resulted from the biological and developmental lottery of human reproduction and development. Some will be well suited to the ship's demands, others will not. The first death aboard is a specific and significant event. The first time the community experiences the loss of one of its own in a context where there is no way to bring a body home, no funeral tradition from outside that applies without modification, no cultural script for grief in these specific circumstances. How the community handles this moment, how it creates meaning from loss in the context of the voyage, sets precedents that echo across subsequent generations. The first birth is similarly significant, and probably more so in terms of cultural weight. The first child born in interstellar space, to parents who left Earth on a journey that will not end in their lifetimes, is the living embodiment of the mission's continuity. This child did not choose the voyage. This child is the first person for whom the ship is not a choice, but simply the world. How the community understands and treats this child, what obligations it acknowledges toward those who did not choose their situation, shapes the ethical culture of the community in ways that persist. The moment when the founding generation's leadership passes to the second generation is the ship's first major institutional stress test. The founders held authority partly from their specific knowledge. They remember Earth, they remember why they came, they carry embodied understanding of the civilization that built the ship, and partly from the conventional authority of age and experience. The second generation's leadership carries none of this specific experiential authority. Their leadership must rest on other foundations: demonstrated competence, institutional legitimacy, cultural credibility. Whether the institutional structures established at departure transfer authority cleanly across this first generational transition depends on how carefully those structures were designed and how well they were embedded in the ship's culture before the transition was needed. Transitions that fail here, where the founding generation's authority collapses into succession crises, rather than passing smoothly to legitimate successors, can be destabilizing in ways that compound across subsequent generations. The historical record of succession crises in isolated communities is not encouraging. The early history of Pitcairn Island, which we have already discussed, involved murderous competition for authority among the founding group. Many intentional communities established by charismatic founders have disintegrated in the period following the founder's death, when the personal authority that held the community together could not be transferred to institutional structures. Cults and utopian communities established around specific individuals regularly fail at the succession problem. A generationship must solve the succession problem not once, but repeatedly, every generation. The institutional structures that enable clean succession must be robust enough to survive the diversity of personalities and leadership qualities that successive generations will produce, including generations that contain no obvious leaders, generations riven by serious internal conflict, and generations dealing with major crises that distort the normal functioning of leadership selection. Let us now talk about the question of contact, about what happens if, during the voyage, the ship receives a signal indicating intelligent life elsewhere in the galaxy. The ship has been travelling for 150 years. It is roughly 1/3 of the way to Proxima Centauri. The crew, alive now, has known nothing but the ship. They have inherited a mission that began before them and will end after them. And then, from some direction other than the destination or the origin, the ship's receivers pick up a signal that is unambiguously artificial, a repeating pattern at specific frequencies that no known natural process produces. Not from Proxima Centauri, from somewhere else, from another star, at some angle off the ship's course. What does the crew do with this? The decision they face is extraordinary. They cannot contact Earth in real time. The communication delay makes consultation impossible for any decision that must be made in less than years. They cannot change course to investigate without fundamentally altering the mission. A course change that takes them toward the signal, rather than Proxima Centauri, would require decelerating, reorienting, reaccelerating, adding perhaps centuries to the voyage, or making the original destination unreachable. They cannot convene a global conversation with any larger human civilization. They are the only humans in this part of the galaxy, making decisions that no one else can make for them. And yet, the decision is among the most consequential any humans have ever faced. Contact with extraterrestrial intelligence, the confirmation that we are not alone, would be the most significant discovery in the history of our species. The decision about what to do with that knowledge, made by a few thousand people on an interstellar ship with no possibility of broader consultation, carries a weight that exceeds any authority those people were formerly granted. This scenario is low probability in absolute terms, but it is not negligible, especially if the galaxy contains even a modest number of technological civilizations that have been transmitting for any significant period. And it illustrates a broader truth about the generation ship's governance challenge. The crew will face decisions that the founding generation did not anticipate, and for which the ship's institutional structures provide no guidance. The capacity to make wise decisions under conditions of radical novelty and radical isolation, without recourse to any external authority, is not a supplementary requirement of the generation ship mission. It is central to it. Let us now talk about what the generation ship implies for our understanding of intelligence and civilization more broadly, about what it reveals when we think about it not just as a human project, but as a case study in what any technological civilization attempting interstellar expansion would face. If we are not alone, if the galaxy contains or has contained other technological civilizations, then any of them that attempted interstellar expansion faced versions of the same problems we have been discussing. The specific biological details would differ. The specific cultural forms would differ. The specific technologies would differ. But the fundamental challenges, maintaining a small, isolated community across timescales longer than individual lives, transmitting the knowledge and values required for mission success across generations, sustaining psychological health and social coherence under conditions of radical confinement. These challenges follow from the basic physics of interstellar travel and the basic biology of finite-lived organisms. Any civilization whose members live finite lives and travel at sublight speeds faces the generation ship problem. The specific version of the problem depends on the civilization's biology, their lifespan, their reproductive strategy, their psychological requirements, but the basic structure is universal. Unless a civilization achieves either indefinite lifespan for its members or propulsion close enough to the speed of light to make relativistic time dilation eliminate the generational problem, it faces the challenge of sending communities rather than individuals across the spaces between stars. The difficulty of this challenge, as our analysis has suggested, is severe. This may be part of why the galaxy appears empty, not because intelligence is rare, but because the specific step of establishing multi-star civilizations is harder than it appears, and many civilizations that reach the technological threshold for interstellar travel fail to sustain the social and biological conditions required for multi-generational voyages. This is speculative, but it is grounded in the specific analysis we have done. Every risk category we have identified, genetic, psychological, sociological, technical, is a filter that would apply to any finite-lived species attempting interstellar expansion. Every failure mode we have traced is a failure mode that any such species would face. If even a fraction of these failure modes are consistently realized across many species and many attempts, the galaxy's apparent emptiness becomes less surprising. The generation ship problem, seen from this angle, is not just a future engineering challenge for human civilization. It is a window onto one of the deepest questions in the study of intelligence in the universe. Why the cosmos that should, by calculation, be full of civilizations, appears instead to be silent. And the answer the generation ship suggests is not cosmic catastrophe or alien indifference, but something more prosaic and in some ways more profound. That building and sustaining a community that can survive across the distances between stars is just genuinely, consistently, thoroughly hard. Hard in ways that touch the deepest features of what living, finite, social beings require in order to flourish. Hard in ways that may defeat most attempts. Hard in ways that make success the exception rather than the rule, even for civilizations that have solved every other problem. If that is right, then getting it right, understanding the problem completely, investing in the research required to address it, building the first generation ships on the most solid possible foundation of knowledge, matters more than it might seem. Not just for our civilization's expansion, for the future of intelligence in the universe. Somewhere tonight, under a sky you can actually see, there is a star. Not a metaphor, an actual star, a point of light in the actual sky above you, one of the few thousand visible to the naked eye from wherever you are standing. It is between 4 and a few thousand light years away. It may have planets. Some of those planets may have liquid water. Some of those planets, by the best current estimates, may have conditions compatible with life. And it is completely unreachable by any technology that exists today, or that will exist in your lifetime, or probably in the lifetimes of your children. The distance is not the hard part. The distance is just physics, and physics eventually yields to engineering. The hard part is everything else. The hard part is the question we have been sitting with all night. Whether a small group of human beings cut off from everything that normally sustains human civilization, can remain human, in any sense that matters, across the centuries required to cross that distance? We have followed this question carefully, and what it revealed was not simple. It was not reassuring, nor was it hopeless. It was honest, which is the best thing a question can be. The genetics are real. A founding population of several thousand people, augmented by frozen genetic material, managed carefully across generations. This can probably sustain biological viability for a voyage of several centuries. Probably. With good management and some luck and no catastrophic bottleneck events that no one predicted. The margin is thinner than optimistic treatments suggest and wider than pessimistic ones. The honest assessment is possible, not guaranteed, sensitive to conditions that cannot be fully controlled. The psychology is harder. Long-duration confinement degrades human beings in specific and consistent ways. Reduced motivation, increased social tension, flattened affect, disrupted sleep, cognitive slowing. And the longest isolation study ever conducted was 520 days, which is less than 0.1% of a 430-year voyage. We are extrapolating across multiple orders of magnitude to conditions that have no precedent. The specific psychological challenge of living an entire life in a closed vessel, as someone who did not choose this and cannot exit it, this has never happened, and we genuinely do not know what it produces. The sociology is harder still. Culture evolves in isolation. Values drift. Knowledge degrades. The social structures adequate to one generation may be inadequate to the next. The mission that was chosen by the founders must be transmitted to descendants who did not choose it, through cultural and institutional systems that themselves evolve in ways no designer can fully predict. Whether the community that arrives is recognizably continuous with the one that departed, whether it retains the technical competence and social coherence and purposive orientation required to establish a colony, depends on an unbroken chain of cultural transmission across every generation of the voyage. The engineering is more tractable than any of this. The physics is clear, the requirements are calculable, the solutions are, in principle, findable. But the engineering is only the beginning. You can build a ship that works mechanically and still produce a catastrophic failure of the human systems inside it. All of this is true, and none of it is a reason not to try. Because here is what else is true. Human beings have consistently done things that their predecessors would have judged impossible. The first people who looked at an open ocean and chose to sail into it, with no knowledge of what lay beyond, with technology that seems impossibly fragile in retrospect, with every reasonable probability of dying, were not behaving irrationally. They were expressing something that runs through our species with the consistency of a physical law, the conviction that the horizon is not a limit but an invitation. Every expansion of human range has required some community to bear costs that no individual could fully understand in advance. The first inhabitants of Arctic environments did not know when they moved north into the cold exactly what it would cost them, or exactly what they would find. The first Polynesians to sail east into unknown ocean did not know how far the water went, or whether islands existed beyond what they could see. They went anyway. Some did not survive. Enough did. The generation ship is this same movement at the scale that our technological moment makes available, not the next valley, the next star. Not a gamble of seasons, but of centuries. Not a risk borne by a single expedition, but by a community that must sustain itself across the entire span of the gamble. The question is not whether this is difficult, It is the most difficult thing our species has ever seriously contemplated. The question is whether the difficulty is a reason to turn away from it or a reason to understand it more carefully, to invest in the research that would close the gaps, to take the human problems as seriously as the engineering problems, to build the first chips on the most solid foundation of knowledge that centuries of preparation can provide. Somewhere in the world tonight, there are researchers working on closed ecological systems, trying to understand why Biosphere 2 failed and what a better design would require. There are population geneticists modelling the dynamics of small, isolated populations, trying to understand the minimum viable numbers for multi-generational viability. There are psychologists studying long-duration isolation, trying to understand what the data from 520-day experiments implies for timescales 10 or 100 times longer. There are engineers working on fusion propulsion, on AI systems capable of managing complex autonomous operations, on cryopreservation of biological tissue at scales approaching what a generation ship would require. None of them is building a generation ship. None of them will live to see one built. But each of them is doing the work that makes a generation ship less impossible, closing, millimetre by millimetre, the gap between what we know and what we need to know to attempt this seriously. This is how it has always worked. The generation ship, if it is ever built, will not be the product of a sudden burst of inspiration. It will be the product of centuries of accumulation, of small advances in biology and psychology and engineering and materials science and governance theory, each one inadequate by itself, adding up over time to something that works. The people who do this work today will not be remembered for it. They will be remembered, if at all, as footnotes, researchers who contributed to a program that took centuries to bear fruit, working on problems that seemed arcane or premature or hopelessly speculative in their own time. This is how most important work goes. The scientists who developed the foundational understanding of genetics that makes modern medicine possible died before any of the applications existed. The mathematicians who developed the calculus that makes orbital mechanics calculable never imagined rockets. The researchers who spent careers studying the behavior of bacteria in unusual conditions laid the groundwork for biotechnologies they never lived to see. The generation ship will be built, if it is ever built, by people who never met the researchers who made it possible. This is not a failure of recognition. It is how knowledge accumulates. It is how civilizations project their reach across time. There is a star out there tonight, probably several of them, probably dozens or hundreds within reach of a serious interstellar program, given enough time and enough technological development. And somewhere on Earth tonight, probably already born, possibly already studying something relevant, is a person who will contribute something essential to the understanding that eventually makes the first generation ship possible. They do not know this yet. They may never know it. The connection between their work and the ship it enables may not be visible until after they are gone. This is what civilizational projects look like from the inside. Not heroic moments of individual decision, but the slow accumulation of understanding by people who are doing their work in the ordinary way, in ordinary time, without full visibility into where it is going. The generation ship is centuries away. The research that makes it possible is not. That star is still there. It has been there for billions of years. It will be there when the ship that eventually reaches it is not yet designed, when the civilization that builds it is not yet the civilization it will need to be, when the children who will live and die on the voyage are not yet born. It is patient in the way that only things measured in billions of years can be patient. We are the ones who are not patient. We are the ones who look at the distance and feel it as an invitation rather than a barrier. That feeling, unreasonable, impractical, genetically ancient, is probably the most important thing about us. It always has been.